Imagine the planet at night, glowing faintly with the crackle of unseen voices. From the first spark gaps and crude radio transmitters of the early 20th century to the vast radar pulses of the Cold War era, humanity has been whispering into the void without intending to. These whispers are not soft. Each radio tower, each broadcast television station, each radar dish guarding against aircraft, throws energy upward and outward. Unlike the light of cities, trapped close to the ground by atmosphere and curvature, these signals pass straight through the air and spill into space. They race away at the speed of light, forming an ever-expanding bubble of information that has now reached well over 100 light-years in radius. To an observer in that bubble, the Earth is no longer a silent blue marble. It has become a source of structured noise, unnatural in its patterns, suggestive of intent. At first, the leakage was faint, low-power transmitters, crackling messages that faded into static almost as quickly as they were sent. But by the mid-20th century, powerful military and civilian radars were pushing pulses into the sky that dwarfed the strength of ordinary broadcasts. The famous Arecibo dish in Puerto Rico, before its collapse, was capable of transmitting signals that could, if aimed at a nearby star, be detected with a similar dish, even dozens of light-years away. That capability was rarely used, but once in 1974, a deliberate message was sent toward a globular cluster. Whether anyone was there to hear it is another matter. Even without such deliberate attempts, the sheer quantity of human radio leakage became a beacon. The physics of this leakage is straightforward and unforgiving. Each wave spreads out as a sphere, the energy diluted as the surface area grows. The power, at any point, decreases as the square of the distance. A radar pulse powerful enough to light the sky at Earth's surface becomes almost indistinguishable from background static after crossing 100 light-years. Cosmic space is not a clean vacuum. Interstellar plasma and dust scatter and disperse the signal, spreading it out and smearing the information. To detect a faint human broadcast across the stars would require either an immense receiver dish, far larger than any humanity has built, or a patient listener willing to integrate the signal over many hours or even years to tease out faint periodicities. Still, we must consider scale. If a civilization already possesses receivers kilometers across, possibly even arrays in orbit or on their moon equivalents, then human leakage may stand out against the cosmic background. To them, our earliest radio stations from the 1920s would already be arriving, faint but regular, forming a thin shell of information, now a century old. Civilizations within 100 light-years could already be aware of Earth's chatter. Civilizations beyond that limit would hear only silence, for our light cone has not yet reached them. The map of stars within that 100 light-year sphere contains thousands of stars, many with planets, some, perhaps, with watchers. It is not only radio and television that matter. Humanity has hurled probes outward, each carrying transmitters that once called home. The Voyager craft with their golden records, the Pioneer probes with their plaques, the more recent New Horizons, all pushed weak signals that traveled far but dwindled rapidly. At interstellar distances, their transmissions blur into undetectable static unless the receiver is designed with almost unimaginable sensitivity. Even laser experiments, though highly directional, might stand out if another civilization were in the line of fire. The 20th and 21st centuries have been full of unintentional beacons. For an alien observer, the Earth is not a silent world. It is wrapped in a cocoon of artificial radio waves, radar pulses, and spacecraft whispers. Each carries information not only about the existence of intelligence, but also about the stage of our technology. The exact detectability is a question of distance, sensitivity, and intent. A nearby civilization could already know we exist simply by listening carefully enough. A distant one would need either technology far beyond our imagination or patience extending over millennia. The question that lingers is this: if someone has been listening, what story do these signals actually tell about us? Are they mere bursts of energy, meaningless noise? Or can they be unraveled into patterns that reveal culture, language, even thought? The answer leads us into the next question, where physics gives way to interpretation. If our signals can be detected, what would they actually tell an alien listener? The first thing any alien receiver would notice is not the voices of actors in a radio play or the commentary of a sports match, but the raw power levels and modulation schemes. Our signals are structured. Natural astrophysical sources rarely show the sharp carriers and repeating patterns of amplitude modulation or frequency shifts. An alien listener would not need to understand English or Mandarin to know the Earth is alive with technology. The sudden rise of narrowband carriers in the last century would stand out against the broadband hiss of pulsars and quasars like the gleam of a lighthouse through fog. The leakage would come in layers. Early radio and television broadcasts in the 1920s and 30s were crude and faint, but by the 1950s, Earth was shining with 1 million transmitters. Each station was broadcasting continuously, creating a dense forest of signals. Radar, even more intense, added short bursts of high energy that pierced the sky and scattered across the ionosphere into space. Civil defense radars, early warning networks, planetary radar experiments at observatories, all of these together made Earth a unique source of spiky, unnatural emissions. To a sophisticated spectrometer, pattern would be obvious. Yet the reach of those broadcasts is soberingly limited. The strongest analog television signals might be detectable with a giant dish array, perhaps tens of light years away. Beyond that, they dissolve into the background noise of the galaxy. Even the mighty Arecibo pulses would vanish into static after a few hundred light years. The universe is vast, and 100 light years is a mere neighborhood around the Sunday. Out of the 400 billion stars in the Milky Way, only a few tens of thousands fall inside that shell. Any civilization farther than that is deaf to our chatter, at least for now. And there is another complication. As Earth's technology has advanced, the leakage has begun to shrink. Analog television has faded, replaced by digital broadcasting, with lower power and more directional signals. Fiber optics have pulled countless conversations out of the air and into cables. Radar systems have grown more efficient and less wasteful. Humanity has become quieter, not louder. In some bands of radio spectrum, Earth may actually be dimmer today than it was in the 1970s. To an alien listener, the Earth's bright flare of radio energy might appear to rise and then decline. A curious, transient phenomenon, lasting barely a century. This fact is rarely appreciated but critical. The so-called radio window for detecting Earth as a noisy planet may close within another few decades. This raises a fascinating possibility. A nearby civilization that began listening during the 20th century might already have detected us. Another civilization that waits to begin its survey a century from now may find nothing but background static. The story of Earth told through leakage is a brief and flickering one. We are like a match struck in the dark, bright for a moment, then fading into obscurity. Now imagine the technical side of detection. Suppose a civilization only 20 light years away points a radio array at Earth. With dishes kilometers across, or perhaps swarms of smaller receivers spread over their planet or their orbit, they could collect faint signals that no human receiver could ever recover. They could integrate those signals for weeks or months, stacking them to raise the coherent whisper above the hiss of galactic noise. What emerges might be just the bare outlines of carriers and modulation envelopes, not the detailed content. They may know that the Earth is full of transmitters, but not be able to watch a sitcom or listen to a jazz concert. Still, even that outline is telling. They would see that one planet among many radiates structured narrowband emissions that switch on in the 20th century of its timeline. They would see the pulse of radars, the hum of television carriers, the shift from analog to digital. They would infer not only the existence of intelligence, but the pace of technological change. To detect such a pattern is already to glimpse the story of a civilization. The speculative edge lies in asking what assumptions about alien technology are fair. If they have only our current capabilities, then perhaps even the nearest stars cannot hear us. If they are centuries ahead, they might possess radio arrays the size of continents, or even antennas strung across their moon or orbit. If they are millennia ahead, they might deploy sensors that we cannot even imagine, based on physics we do not yet command. The gulf between those scenarios is immense, but we cannot rule any of them out. And so we circle back to the haunting question. Within 100 light years, there are thousands of stars, and perhaps millions of planets. Some fraction may host life, a smaller fraction may host intelligence, and a still smaller fraction may host civilizations capable of listening with patience and precision. If any of those civilizations exist, then our signals are already washing over them. They already know that Earth is not just a rock with an atmosphere, but a place of transmitters and pulses, a place where something has awakened. The thought is both exhilarating and unsettling. It suggests that we may not be alone in our knowledge of ourselves. Others may have noticed us long before we noticed them. Our technology betrays us, advertising our presence without consent, announcing to the galaxy that a young species has emerged. Whether anyone listens and whether they care is another matter. The transition is clear. If our signals are detectable, then the next question is what meaning can be extracted from them. Do they reveal culture, mathematics, or only power levels? Do they betray our fears and our joys, or only our existence? The leap from physics to interpretation is vast, but it is the leap that must be made. If someone out there already knows about us, what exactly do they know? The shell of signals surrounding Earth is already thick with our fingerprints, yet the meaning of those signals depends entirely on who receives them and how they choose to listen. Imagine a world orbiting a star 30 light-years away. To them, our earliest television shows and radio news bulletins are just arriving now, carried across the darkness as faint ripples of order against the background chaos. Perhaps they see the rhythmic pulses of our radar first, then notice the constant carriers of broadcast towers. To them, it is not music or laughter that stands out, but the unmistakable sign of regularity. The universe is filled with noise, but not with such crafted structure. If their technology is limited, they may only be able to register that the planet is alive with narrowband emissions. They might not recover images or voices, but they would know the difference between a silent rock and a transmitting world. If their technology is centuries ahead, perhaps they can peel back layers of the signal. With receivers spanning thousands of kilometers and computing power we can scarcely imagine, they might reconstruct fragments of actual content. The face of a newsreader, distorted but recognizable. The tone of a popular song, faint but traceable. An alien civilization that advanced would not need to guess whether intelligence existed here. They could see and hear it directly. Even so, the difficulty remains immense. The signal is smeared by interstellar medium, weakened by inverse square dilution, and corrupted by interference from our own planet. What seems to us like a strong and clear transmission becomes a whisper by the time it crosses even a few dozen light years. To make sense of it requires patience and assumptions about our coding methods. Without those, the best they could do would be to measure the modulation depth and frequency structure, inferring that some ordered communication is underway. They might never grasp the storylines or the jokes, but they would know that beings on Earth are exchanging complex information. It is also worth imagining how strange we might appear. Our first century of leakage is full of sudden changes. One decade, the air is thick with analog television carriers. The next, they vanish as digital compression and cable dominate. Radar bursts intensify during the Cold War, then settle. To an alien historian watching from afar, Earth's radio shell is a chaotic story of experimentation, rise, and decline. They might wonder whether the civilization that produced these signals is stable or erratic. Perhaps they might conclude, we are volatile, prone to bursts of technological energy, followed by silence. What would they infer about us beyond the fact that we exist? They could measure the rotation of the planet by watching the diurnal cycle of transmission strength. They could map our geography by noting which regions produce signals at which times. They might even detect that our transmissions are clustered in the northern hemisphere, hinting at where our population is concentrated. All of this is visible without ever decoding a single word of content. The energy patterns themselves reveal a civilization. There is a sobering mirror here. If we can imagine them seeing us this way, then we must ask what we would see if roles were reversed. If we pointed our radio telescopes at a nearby star and detected a faint, structured whisper, how much could we truly say about its source? We could confirm intelligence. We could guess at energy levels and technology. But culture, language, and intention would remain hidden. Without context, the content is noise, And so the first chapter of this story closes with a paradox. Humanity has been broadcasting into the void for just over a century, a blink in cosmic time, yet already enough to create a detectable bubble, reaching out 100 light years. Any nearby civilization with advanced sensors could already know that Earth is home to intelligence, but knowing that we exist is not the same as knowing who we are. The leap from detection to interpretation is vast, and it is this leap we must now examine. If others are listening, what would they actually learn about us? From the perspective of the cosmos, Earth is not merely a ball of rock orbiting an ordinary yellow star. It is a transmitter, a beacon wrapped in signals that radiate outward in every direction. These signals do not simply reveal existence. They contain clues about atmosphere, chemistry, and civilization. To an alien civilization with sufficient patience and equipment, the Earth is telling a story whether we wish it to or not. The first layer of that story is written in the light of our atmosphere itself. Long before a single broadcast left the planet, the gases surrounding Earth betrayed the presence of life. Oxygen, ozone, and methane combine in unstable ways that only biology can sustain. For billions of years, the spectral fingerprint of our sky has carried those markers outward, visible to anyone who cared to look. With the arrival of industry in the last 2 centuries, a new layer has been added. Chlorofluorocarbons and other artificial compounds now lace the atmosphere, producing spectral lines that nature does not make. These technosignatures are subtle, yet in principle detectable, with instruments far beyond what we currently possess. But what of the leakage itself, the radio and radar that began in the early 20th century? To an alien receiver, the sudden arrival of narrowband, high-frequency emissions would stand out sharply. Unlike natural radio sources, our signals are concentrated in specific frequencies, modulated in complex but repetitive ways. Even without decoding, the mere presence of these structures signals technology. If the observer is close enough and their instruments strong enough, they might attempt to reconstruct more detail. Perhaps they could recover the cadence of a voice, the rhythm of a song, or the flickering frames of an old broadcast television signal. It is not certain that they would succeed. To decipher the content requires assumptions about the encoding scheme and the cultural context. A television transmission from the 1950s, when smeared by interstellar noise, may be nothing more than a distorted set of patterns. To us, those patterns mean a comedy skit or a news bulletin. To them, it may be unintelligible shapes. Without the Rosetta Stone of shared context, full decoding may be impossible. Yet even partial recovery would speak volumes. We would know we use images, we synchronize signals, we repeat messages at regular intervals. These are unmistakable signs of intelligence. Consider also the possibility of night-side detection. The Earth's dark hemisphere is not truly dark. From orbit, it glitters with artificial lights, a feature that is invisible to natural planetary processes. At present, our telescopes cannot detect such city glow on exoplanets, but future generations of instruments may. An alien civilization, already centuries ahead, may have achieved that feat long ago. To them, Earth might shine not only by reflected sunlight but by its own patterned brilliance. The arrangement of cities, the flicker of seasonal variations, even the dimming of lights during crises, could be visible to their patient eyes. The question of what they truly learn rests on the scale of their technology. If they are only slightly more advanced than us, they may detect little more than excess energy and spectral anomalies. If they are millennia beyond, they may be able to reconstruct entire broadcasts, watching our dramas and hearing our music. The difference between these scenarios is profound. In one case, we are merely an interesting blip on the radio spectrum. In the other, we are an open book. This leads to an unsettling thought. If they can hear us in detail, then they already know more about us than we know about them. They may have watched our wars, our celebrations, our errors. They may know our languages, symbols, even our myths. They may know us intimately, while remaining invisible to us. It is a one-way mirror, in which we are the actors and they are the hidden audience. And yet there is a chance that the opposite is true. Perhaps even the nearest star systems cannot recover meaningful content. Perhaps all they see is a strange noise source, rising and falling, with no clear message inside. In that case, our privacy remains intact by the simple mercy of physics. The galaxy may be deaf to our stories, hearing only the faint drumbeat of our technology. The transition to the next question is inevitable. If others can see our footprint, the next matter is not whether they understand it, but whether they care. Detection alone does not guarantee interest. What motives would drive an alien civilization to observe, study, or ignore a young world like ours? The answer lies not in physics, but in the tangled logic of behavior and intention. The signals leaving Earth do not present themselves as a polite message or a carefully encoded greeting. They arrive messy, layered, and full of contradictions. To an alien observer, the first impression might not be the content of any single broadcast, but the sheer diversity of the transmissions. Some are steady and precise, like navigation beacons or time signals. Others are chaotic, like commercial radio chatter or scrambled military channels. To a civilization with advanced instruments, this jumble is itself meaningful. It reveals a species that has created a complex information environment, one in which countless voices speak at once without central coordination. From this noise, patterns would emerge. They would notice that most signals come from one hemisphere more than the other, suggesting an uneven distribution of technology and population. They would detect seasonal variations, as holidays and events create bursts of activity at regular intervals. They might even catch the cyclical patterns of global phenomena, like the Olympics or political elections, which repeat with predictable timing. Such observations would not require them to understand a single word. The rhythms of civilization are written into the structure of its transmissions. The atmosphere adds another dimension to this picture. Long before the first radio broadcast, Earth was already shouting through chemistry. Ozone in the stratosphere shields life from ultraviolet radiation, but it also leaves a signature in the spectrum that can be measured across interstellar distances. Methane, produced largely by biological processes, exists alongside oxygen in a disequilibrium that physics alone cannot sustain. These clues are not subtle. Even human astronomers are now reaching the threshold of detecting similar biosignatures on exoplanets many light years away. A civilization with superior instruments could have done so long ago for Earth. To them, our atmosphere might be as revealing as our radio noise. When industry began reshaping the planet in the 19th and 20th centuries, another layer of information was added. Coal and oil combustion filled the air with carbon dioxide at unprecedented rates. Later, synthetic chemicals like chlorofluorocarbons appeared, substances with spectral lines that nature never produces. These artificial compounds could be seen as a planetary fingerprint of technology, a techno-signature layered atop the biosignature. If aliens can detect such lines, they already know that Earth harbors not just life but industry. Yet even with such data, interpretation is treacherous. Imagine trying to reconstruct the story of a civilization from faint signals and spectral fingerprints alone. Could one distinguish between a world in the midst of industrial growth and one in decline? Could one see the difference between a planet transitioning to renewable energy and one collapsing into silence? The signals tell us something, but they do not tell us everything. They are clues, not narratives. Some thinkers have speculated that if aliens could decode our television or radio broadcasts, they might sit in their observatories watching our old programs. But this assumes a level of technological advantage that we cannot confirm. More importantly, it assumes that content can be interpreted outside of context. A sitcom or a news broadcast is meaningful to us because we share the cultural framework that produced it. To an alien mind, the same images might be incomprehensible. A battle scene could be mistaken for reality, a cartoon for madness, a commercial for ritual. Without the cultural Rosetta Stone, the meaning of our signals might be forever closed to them. Still, even without meaning, there is message. They would see that we use imagery, that we transmit speech, that we modulate signals in consistent patterns. They would see that we build structures not of stone or steel but of information. That fact alone is extraordinary. It would tell them that Earth is inhabited not only by life, but by intelligence that seeks to communicate across its own surface. This leaves us with a strange balance. On one hand, the signals are a crude and unreliable way of announcing ourselves, distorted and fading as they move outward. On the other, they are enough to mark us as unique in a galaxy where silence seems to be the rule. We may never know how much detail can truly be recovered by those who listen, but the certainty is that they can at least detect that something unusual is happening here. And so the second chapter turns toward motive. If others have the ability to notice our footprint, the more important question is whether they would choose to. Why would they spend resources on monitoring a young species on a small planet? Would they see us as a curiosity, a potential danger, or something too trivial to matter? The physics of leakage is clear, but the psychology of attention is not. That is the frontier we now approach. The puzzle of what our signals reveal is sharpened by one unavoidable truth. To know us through these emissions is to know us in the past. Every transmission races outward at the speed of light, meaning that an observer 50 light-years away is watching Earth as it was in the 1970s. An observer 100 light-years away sees the first decades of our radio dawn with crude broadcasts and booming analog carriers. None can yet see our present, only our history unfolding in a moving shell of information. This delay means that aliens who already know of us know only earlier versions of us, frozen snapshots carried outward on the tide of photons. This time, lag matters deeply. They would not see the internet age, not yet. They would not see the rise of satellites filling low orbit with chatter, or the shift to digital compression that has made our planet quieter. They would not know our current political crises or cultural revolutions. What they would see are the events and broadcasts of decades past. If they attempted to judge our civilization on that basis, their conclusions could be dramatically outdated. They might think us still divided by empires long gone, still fighting wars that have since ended, still broadcasting music styles that now sound quaint. To them, we are a time capsule drifting outward, our present self hidden until centuries pass. Yet the delay cuts both ways. To us, a signal from a distant civilization would also be ancient. The knowledge that alien observers may see only our past is not a weakness, but a symmetry. It is the natural rhythm of communication in a vast galaxy, where every exchange is stretched across lifetimes. This recognition brings a sobering humility. If they know us imperfectly, and we in turn would know them imperfectly. Still, even fragments of knowledge can be powerful. An alien civilization that has confirmed our existence, even at the most basic level, might view us with a mixture of curiosity and caution. They would see a species just awakening into technology, noisy for a brief century, and then already growing quieter. They might wonder whether we will continue to advance, or whether we will burn out quickly. They might decide to keep watching, waiting for clearer signals, or they might dismiss us as too young and fragile to matter in the long run. The possibility that they could have seen not only our biosignatures but also our technosignatures carries an even greater implication. If their telescopes are powerful enough, they may have already noticed the growing carbon dioxide levels in our atmosphere, a sign of industrial activity that is altering the climate. They may have drawn conclusions about our stewardship of our planet, perhaps even questioning whether we will survive our own technological adolescence. In this sense, our atmosphere is an open book, telling a story we ourselves sometimes struggle to face. One can imagine the unsettling intimacy of such knowledge. While we debate among ourselves about energy and sustainability, they might already have run simulations predicting our trajectory. They might know whether Earth is headed for a stable balance or a collapse. They may see us not as a mystery, but as a predictable outcome, our fate written in the spectral lines of our sky. Whether they interpret this with sympathy, indifference, or contempt depends entirely on their motives. And so we arrive at the edge of speculation, where physics gives way to behavior. We know what can be detected, we know what patterns exist, but we cannot know what significance those patterns hold for another mind. The real question is not only what our signals say, but why anyone would bother to listen at all. The act of listening requires motive, and motive is shaped by perspective, culture, and intent. This is where the narrative turns. If they already know about us, The pressing mystery is not the physics of detection, but the psychology of observation. What would drive another civilization to watch a world like ours? Would it be scientific curiosity, the cautious instincts of survival, or a philosophy of non-interference? The answers lie not in wavelengths or spectral lines, but in the deeper realm of motive, which is the subject of what follows. Picture again that expanding shell of signals rushing outward from Earth. To us, it is an accident of technology, a byproduct of communication and defense. To anyone beyond our sky, it is a flare announcing the presence of a new player. The physics of detection explains what they could see, but it does not explain why they would choose to look. This is where speculation sharpens, because the question of motive is not written in mathematics. It is written in behavior, and behavior is shaped by the same mixture of curiosity, caution, and necessity that drives us. If we mirror the scenario through human eyes, the most obvious motive is scientific reconnaissance. When our astronomers detect an unusual planet, we point every instrument we have to learn more. We analyze its light, search for chemical fingerprints, and imagine what it might be like to stand there. Why would another civilization act differently? To them, Earth might be a rare and precious example of a world in transition, a planet where life has leapt into intelligence. To study such a planet is to study the very process of cosmic evolution. For scientists, there could be no greater prize than watching another intelligence awaken. Yet science alone may not explain everything. Motives can also be ecological. Imagine a galaxy filled with fragile biomes and countless paths to collapse. A civilization that has endured long enough to master the stars might see it as duty to monitor younger species, not to control them, but to ensure they do not destroy themselves too quickly. The very act of watching could be a form of guardianship, not intervention but vigilance, like ecologists on Earth who track endangered species from a distance. From this perspective, observing Earth could be an act of conservation. There is also the possibility of caution. To discover a new intelligence is to discover a potential rival. Even a young species with crude technology could one day become dangerous. The logic of game theory applies here. If survival is at stake, then every rational actor watches closely for new entrants. The presence of radar and radio would not only intrigue, but also alarm, because they signal the first steps towards spacefaring capacity. To monitor Earth could therefore be a defensive measure, ensuring that no surprise arises in the galactic neighborhood. But motives are rarely pure. Human history shows that observation often mixes curiosity, caution, and exploitation. When explorers first encountered new lands, they mapped them not only to study but to assess resources. To an alien civilization, Earth may be interesting not only as a biosphere, but as a repository of raw materials. Its oceans, metals, and orbital position are assets, and even if they have no intention to harvest them now, knowledge of their existence could be valuable. Observation could serve as reconnaissance in a broader strategy of resource management. One should not underestimate the possibility of indifference. To us, every discovery of life would be monumental, but to a civilization for whom life-bearing planets are common, Earth may be unremarkable. Our chatter might be faint background noise in a galaxy rich with voices. They might record it without much interest, cataloguing Earth as one among many. In this scenario, we imagine ourselves the center of attention, but in reality, we are just another data point. Speculation grows more uncertain when we consider models of alien psychology. They behave like predators, seeing us as prey to be managed. Would they behave like scientists, carefully recording our development without interference? Would they act as passive observers, content to know, but not to engage? Each model says more about us than about them, because we are forced to draw analogies from human behavior. The danger of anthropocentrism lurks here, the temptation to imagine them as reflections of ourselves. Yet we have no other guide. The range of motives shapes the possible methods of observation. If they are scientists, they might use subtle remote sensing. If they are cautious, they might employ stealth probes to track our progress more closely. If they are indifferent, they may not invest heavily in monitoring at all. In each case, the physics of detection is the same, but the purpose behind it changes everything. As we step into this uncertain territory, one truth remains constant. Motive determines method. How they choose to watch us, whether from afar or up close, depends entirely on why they are watching at all. And so the question of motive is not an end, but a transition. To understand what aliens might already know about us, we must now imagine the ways in which they could be watching. That is the frontier of the next part of the story. The spectrum of possible motives is wide, and each one paints a different picture of how a civilization might regard Earth. To linger on the scientific motive, one must remember how we treat our own discoveries. When astronomers found the first exoplanet in the 1990s, it set off a revolution. Each new detection since then has been catalogued with care, studied for orbital dynamics, atmospheric possibilities, and signs of habitability. The mere hint of oxygen or methane on a distant world would ignite entire research programs. It is only reasonable to assume that a civilization far more advanced would act with similar, if not greater, enthusiasm. For them, Earth would be a living laboratory, a natural experiment in the development of intelligence. But scientific observation can easily blur into surveillance. What begins as curiosity may transform into a program of long-term monitoring. A civilization might decide to track our emissions systematically, building up a record of our progress decade by decade. They would note when our broadcasts began, how they grew, and when they started to decline. They might chart our use of fossil fuels, detect the rise of greenhouse gases, and compare it with their own historical patterns. If they are scientists, they may be studying us to test theories of cultural evolution or planetary change. To them, we are data, a chance to refine models of how civilizations rise or fall. If caution is their guiding principle, the tone changes. The discovery of a species beginning to transmit into space may trigger alarms. Even if Earth poses no present threat, the logic of game theory suggests that it could in the future. From this perspective, ignoring us would be irrational. Any rational actor would want to know whether we are likely to expand, whether we are violent, whether we are stable. Surveillance then becomes not a matter of curiosity, but of security. They might adopt a strategy of distant monitoring, much as nations on Earth track the weapons development of potential rivals. They might choose to remain hidden while observing closely, preferring not to reveal their existence until they understand our intentions. A motive rooted in resource assessment would follow a different line of logic. For a species that travels the stars, resources may not be scarce in the way they are for us. Yet they are not meaningless. The abundance of liquid water, organic molecules, and metals on Earth may be of interest, if not for immediate use, then for future planning. To assess resources requires mapping and monitoring. Even if they never intend to intervene, the information is valuable. Our world could be logged in a galactic catalogue, not unlike the maps we make of asteroids and comets, filed away for the time when it might matter. The possibility of indifference is harder for us to accept, because it diminishes our importance, but it may be the most realistic scenario. If the galaxy is teeming with civilizations, each producing its own flare of radio noise, then Earth is simply one more among many. Our chatter might not stand out, our biosignatures might not be unique. We may be interesting, but not exceptional. In this case, the motive to observe may be weak or non-existent. They might record us in passing, then turn their attention elsewhere. Our signals may matter no more to them than the call of a single bird matters to an ecologist walking through a rainforest. Anthropocentrism complicates every attempt to imagine motives. We think of alien behavior. We inevitably project our own history onto them. We recall explorers who sailed across oceans, sometimes studying, sometimes conquering. We remember scientists who observed animal species, sometimes protecting, sometimes exploiting. We know empires that expanded for resources and cultures that chose isolation. Every scenario we imagine is drawn from this palette. But alien minds may be shaped by conditions we cannot imagine, with values and drives alien to our own. The danger is that we mistake our reflection for a prediction, and yet, despite the risk of projection, it is all we have. To make sense of alien motives, we must use the models available to us. That means drawing from our own history, our own psychology, our own logic. We cannot claim certainty, but we can explore possibilities. We can ask which motives are consistent with survival, which with curiosity, which with caution. And from those possibilities, we can construct scenarios that guide our thinking. The next step is to imagine how motives translate into action. If they watch us as scientists, how do they do it? If they watch us with caution, what methods would they choose? If they are indifferent, how would that show itself in their behavior? The line from motive to method is direct, and it is along that line we must now proceed. If their motive is scientific curiosity, the methods of observation might be gentle and elegant. They could place telescopes in orbit around their own star, tuned precisely to catch the faintest changes in our emissions. They could monitor our atmosphere for subtle shifts, building a profile of our biology and technology without ever approaching us. The goal would not be to interfere, but to accumulate knowledge. They might watch for centuries, content to let our story unfold naturally. To them, time may be abundant, and patience the most valuable tool. If their motive is caution, the methods might lean towards stealth and comprehensiveness. They could deploy remote probes to the edge of our system, watching silently from the darkness. These probes might relay information about our broadcasts, our rocket launches, even the heat patterns of our cities. The watchers would remain invisible, taking care not to trigger our awareness. Just as nations on Earth send satellites to observe one another without consent, a cautious civilization may already have chosen to watch us directly, but secretly. To them, the risk of revealing themselves might outweigh the benefit of open contact. A resource-focused motive could produce yet another style of observation. Their instruments might map not only our emissions, but our geology, our oceans, our climate. They could study mineral signatures from orbit, track ocean chemistry, or even deploy robotic surveyors to nearby asteroids to assess the system's wealth. Observation in this mode is reconnaissance for potential use. Whether they ever intend to exploit those resources is another question. The logic of cataloging them is undeniable. Indifference, however, would manifest as absence. They may have detected our signals long ago, classified us as an emerging civilization, and simply moved on. To them, we are a curiosity, but not a priority. Our bubble of radio leakage passes across the galaxy, and they record it as one among countless others. In this scenario, no probes are sent, no special instruments are aimed at us. No resources are invested in careful monitoring. Their motive is to acknowledge, but not to dwell. This possibility may be the most difficult for us to accept, because it denies us the central role in a drama we long to believe we are part of. The reality may be a mixture. Different civilizations may hold different motives, or the same civilization may change its motives over time. Curiosity may give way to caution, indifference may evolve into interest, or science may blend with strategy. Just as human motives are rarely singular, alien motives may be layered and complex. To assume only one is to oversimplify a spectrum of possibilities that may be as wide as the stars themselves. Yet whatever their reasons, the decision to watch or ignore us shapes the story of contact. If they are watching, then they already know something of us, however incomplete. If they are indifferent, then we may remain unseen despite our best efforts. In either case, the next question is not only why they might observe, but how they would carry out that observation. Motive leads directly to method. To understand whether aliens already know about us, we must explore the methods they might use to watch us without ever being seen. To imagine how another civilization might be watching us, we must first step into their vantage point. Picture the Earth from afar, a blue and white sphere, spinning against the blackness of space. The first impression is visual, the way starlight filters through our atmosphere, scattering into spectral lines that betray oxygen, ozone, methane, and carbon dioxide. With a powerful enough telescope, they could read these lines with clarity. Human astronomers already perform such measurements on exoplanets using the technique of transit spectroscopy, where a planet crosses the face of its star and a small fraction of the starlight passes through its atmosphere. Even with our crude instruments, we can detect broad hints of water vapor and sodium in the skies of distant worlds. An alien civilization with equipment a few centuries ahead of ours could have been reading Earth's atmospheric chemistry for millennia. They would have known we were alive long before we ever broadcast a single signal. But to move beyond biosignatures into technosignatures requires sharper eyes and ears. The most straightforward method is radio observation. As Chapter 1 described, our signals radiate outward and form a shell of information already 100 light-years in radius. A radio array the size of a small continent or a swarm of orbital receivers, synchronized into one vast instrument, could pick apart the faintest whispers from Earth. If they are willing to integrate over time, stacking signal upon signal, they could amplify the faint carriers until they rise above the galactic background. What emerges may not be a clear voice or picture, but enough to recognize a planet wrapped in structured noise. The limits of such detection are governed by physics we understand well. The inverse square law ensures that every doubling of distance reduces signal strength by a factor of 4. Interstellar plasma causes dispersion, stretching signals and smearing their patterns. At hundreds of light years, even our most powerful radars dissolve into the hiss of space. Yet there are tricks an advanced civilization might use. They could deploy vast interferometers, linking antennas across their star system to create baselines, millions of kilometers wide. With such an array, the angular resolution and sensitivity would dwarf anything we can achieve, making our faintest emissions stand out like embers in a night sky. But perhaps they would not rely solely on radio. Neutrinos, nearly massless particles that stream from nuclear reactions, offer another window. Human experiments like Super Kamiokande and IceCube already detect neutrinos arriving from the Sun and distant supernovae. An advanced civilization might have constructed detectors orders of magnitude larger, capable of measuring neutrinos from industrial processes on other worlds. Our nuclear reactors produce streams of antineutrinos, subtle but distinct, to a detector vast enough, buried deep beneath alien oceans or ice sheets. These could be the unintentional markers of a civilization's power generation. Unlike radio waves, neutrinos are not absorbed or scattered easily. They pass through stars and planets almost unhindered. If aliens are listening in neutrinos, then our reactors are already whispering across the void. There are other exotic possibilities. Gravitational waves, ripples in space-time first detected by humans in 2015, could be harnessed for communication or surveillance. Human detectors like LIGO can sense the merging of black holes across billions of light-years. An alien civilization might build far more sensitive instruments, able to detect the subtle ripples caused by the movement of massive spacecraft or the industrial manipulation of planetary systems. Earth does not yet generate detectable gravitational waves through its technology, but our rocket launches and orbital movements, scaled up over centuries, could one day leave signatures. If they have such instruments now, they might already be aware of our smaller disturbances. Optical and infrared observations offer another suite of methods. From afar, Earth glimmers not only with reflected sunlight, but with thermal emissions. Our cities, our industry, our agriculture all alter the planet's energy balance. A sufficiently advanced telescope could map these anomalies. It could see the brightening of city clusters at night, the thermal excess from industrial centers, the changing albedo as forests are cleared and deserts expand. Such monitoring would not require proximity. With telescopes placed in orbit around their own star or even in deep interstellar space, they could gather enough photons over decades to assemble detailed maps of Earth's surface activity. And then there are probes. The possibility of directed probes sent to linger in our system cannot be dismissed. These could be long-lived machines parked at stable gravitational points, like the Earth-Sun Lagrange points, or hidden in the asteroid belt, or resting silently on the lunar far side. Human thinkers call them Bracewell probes, after Ronald Bracewell, who suggested the idea in the 1960s. Such machines could watch silently for centuries, transmitting home only when triggered. If their motive is caution or scientific interest, probes offer a way to observe us directly without risking exposure. They could monitor our radio spectrum up close, track our rocket launches, and even sample our atmosphere for chemical changes. And because they could be made to hibernate, they might remain unnoticed for millennia. The unsettling reality is that the methods available to an advanced civilization multiply with every increment of technology. What seems fantastical to us, vast neutrino arrays, planet-sized interferometers, gravitational observatories, might be routine to them. We cannot assume our limitations are theirs. And if they have these methods, then their picture of Earth is far richer than we imagine. The thought circles back to a haunting possibility. If they are watching us, we may already be under observation by means we cannot detect. We may be studied from afar with instruments beyond our comprehension, or we may be monitored up close by machines hidden in plain sight. The question is not only what methods are possible, but which ones are most likely, given their motives. And that is the path the narrative must now follow. The question of method is not a question of imagination alone. It is bound to the physics of what is possible and the logic of what is efficient. If a civilization 100 light-years away has noticed our radio leakage, they must decide how much effort to devote to following up. To them, we may be one of dozens of young civilizations flickering into view at any given time. That alone forces choices. Do they monitor all equally, or select a few? Do they invest in long-range observation alone, or risk placing machines close to our world? Each method reveals its own advantages and its own dangers. Radio observation is the most conservative path, and perhaps the most likely. From their own star system, they can continue to monitor us without ever risking detection. They can watch our emissions rise and fall, record our spectral lines, and plot our trajectory as a technological species. The costs are minimal compared to interstellar travel, and the risk of exposure is nearly zero. This method aligns well with motives of scientific curiosity or cautious surveillance. It is distant, efficient, and safe. Yet radio alone leaves gaps. It tells them that we exist and are transmitting, but it does not give them a detailed picture of our environment. For that, more intimate methods may be required. Imagine an interstellar probe the size of a small spacecraft, accelerated by powerful propulsion systems across the void to our solar system. Such a craft might take decades or centuries to arrive, but civilizations older than ours by millennia can afford such timescales. Once in our system, the probe could hide in the asteroid belt or behind one of the moons, silently listening. Its advantage would be proximity. With sensitive receivers just millions of kilometers away, it could hear every broadcast, decode every modulation, and perhaps even map the surface of our planet with radar or optical instruments. The moon offers particularly enticing hiding places. Its far side is permanently shielded from Earth's radio chatter, making it a natural sanctuary for clandestine instruments. A probe hidden there would remain invisible to us unless we happened upon it directly. Other stable gravitational zones, such as the Earth-Sun Lagrange points, provide equally convenient parking spots. These locations require little energy to maintain position, allowing a probe to linger indefinitely. Human astronomers already propose such sites as staging grounds for our own future telescopes. An older civilization may have been using them for observation for centuries or more. There is also the prospect of von Neumann probes, self-replicating machines that can repair themselves and multiply using local materials. A civilization that deploys such probes need only send one. Once established, it can create copies of itself, spreading throughout a star system while keeping watch. These machines could be small, efficient, and nearly impossible to eradicate. If such probes exist here, they may already be spread across our system, embedded in asteroids, hidden in the Kuiper Belt, or even resting silently on the ocean floor. The absence of clear evidence does not disprove their existence. It only means we have not looked carefully enough, or that their design is stealthy by intent. Less speculative are optical and infrared methods. A civilization with telescopes positioned in interstellar space could study the Earth continuously without ever leaving home. By collecting the faint glow of our night side, they could measure artificial illumination. By tracking thermal emissions, They could identify the waste heat of industry. By mapping seasonal changes in vegetation from afar, they could follow the rhythms of our agriculture. All of these observations are possible in principle with physics we already understand. We ourselves dream of building kilometer-sized telescopes to detect such signals on exoplanets. An older civilization may already possess them, and may have been watching Earth this way for generations. The technological edge may go still further. If they possess instruments sensitive to minute gravitational perturbations, they could detect spacecraft leaving our planet, measuring the small wobbles they impart on nearby bodies. If they command quantum sensing technologies far beyond our own, they might even use entanglement-based detectors to watch in ways we cannot imagine. To us, these methods are still dreams, but to them, they may be routine, no more exotic than a radio telescope is to us today. One must not forget, however, the problem of intent. Every method carries a signal about the watcher as much as about the watched. A probe in our system risks eventual discovery, and discovery reveals presence. A vast telescope array pointed at Earth may eventually be inferred from the way it blocks or redirects light. Even indifference leaves traces, if only in the form of recorded silence. The choice of method is therefore never neutral. It is shaped not only by what is possible, but by what the watchers are willing to risk. This brings us to the question of concealment. If they are indeed observing us, do they wish us to know? If the answer is no, then their methods must be carefully chosen to avoid exposure. That implies stealthy probes, passive remote sensing, or techniques so far beyond our comprehension that we cannot even conceive of them. If the answer is yes, then their methods might one day tip their hand, allowing us to notice their presence. Until that day comes, we remain uncertain, caught between physics and speculation. And so, as we chart the methods by which they could watch, the story leads naturally to a deeper question. Where are they watching from? Are they distant, content to observe faint traces of our biosphere and radio chatter? Or are they nearby, concealed in our cosmic backyard, their instruments already tracking us in detail? The answer to that question shifts the entire landscape of possibility, and it is the threshold we must now cross. If the choice of method reveals motive, then the question of distance reveals perspective. A civilization watching from hundreds of light years away must be patient, content to piece together faint signals smeared by time and distance. Their picture of us is blurred, a faint silhouette of a civilization just awakening into technology. But a civilization that chooses to watch from nearby could know us with unsettling intimacy, perceiving details we ourselves do not track. The gulf between these vantage points is immense, and each carries its own implications. Consider the watchers who remain distant. They point colossal radio arrays at Earth, measuring the rise and fall of our emissions over decades. They log the increase in carbon dioxide in our atmosphere, track the disappearance of ozone, and chart the seasonal oscillations of vegetation across our continents. Their data are precise but limited. They see trends, not individuals. They can infer the existence of technology, but not the shape of a city block or the decision of a single leader. Their knowledge is broad and abstract, the knowledge of a scientist studying a planet from afar. For them, Earth is an entry in a catalogue, a case study in the evolution of civilizations. Now consider the possibility of nearby probes. If such machines are hidden in our system, they could see everything we see, and more. A probe stationed at a Lagrange point could monitor every launch into orbit, track every satellite, and listen to every unencrypted transmission. A probe buried on the lunar far side could eavesdrop on our radars without our knowing. A machine in orbit around Jupiter or drifting among the asteroids could observe us for centuries, transmitting its data home by narrow beams invisible to us. If such watchers exist, they may already have libraries of information on human culture, politics, and science. They may know our languages, our conflicts, even our private moments, in ways that distant observation could never provide. The troubling question is whether we would notice. Human technology is still clumsy in its search for subtle artifacts. We have mapped only a fraction of near-Earth objects. With high precision, we have scanned the lunar surface, but not with the resolution or persistence to guarantee that no probe is hidden there. Our telescopes sweep the skies, but our ability to detect a small machine, deliberately engineered to hide, is limited. The unsettling possibility is that we could already be observed by technology in our backyard, and yet remain ignorant of its presence. But not every method requires such cloak and dagger. They might employ techniques so advanced that their very operation is invisible to us. Imagine a telescope array constructed of swarms of satellites the size of insects, orbiting their star in coordinated patterns, forming a detector sensitive enough to map our surface temperature from across light years. Imagine neutrino detectors so vast that they can reconstruct the flicker of our nuclear reactors in real time, thousands of light years away. Imagine gravitational wave instruments capable of detecting the launch of our rockets by the ripples they send through space-time. To us, these are speculations. To them, they may be routine. In such cases, there is no question of proximity. They could know us as intimately from afar as they could from nearby. Still, distance and timescale remain the decisive constraints. From 10 light years, they see us as we were a decade ago. From 100 light years, they see us as we were in the early 20th century. From 1,000 light years, they see only a planet with oxygen, long before our species built its first cities. Their knowledge is not of the present, but of our past. The closer they are, the more up-to-date their picture. The farther they are, the more ancient. This time delay means that even the most advanced methods cannot circumvent the laws of light speed. They may know us, but they know us as we were, not as we are. This leads to an irony. The civilizations most likely to know us in detail are those nearby, within a few dozen light years. But those are also the civilizations most likely to alarm us if we discover them, because their proximity would mean they are neighbors in a cosmic sense. Conversely, civilizations farther away may have catalogued Earth for millennia, but what they know is ancient, a record of life and atmosphere long before we evolved. The present is visible only to the close, the distant know only echoes. Thus the spectrum of methods converges on a single theme. The way they watch us and what they can know depends as much on distance and timescale as on technology. The physics sets the limits, the motives set the choices, and the result is a range of possibilities stretching from faint awareness to detailed surveillance. Where on that spectrum reality lies remains unknown, but the framework is clear, and so the chapter turns once more. If they are watching, the crucial question is not only how they do it, but where they are and when they are looking. Distance and timescale shape knowledge, and it is these dimensions we must now explore. To know who could already be aware of us, we must map the geometry of our signals across time and space, and ask what civilizations fall within that expanding sphere of awareness. The cosmos is a theater of delays. Every photon, every radio wave, every particle of light leaves our planet and carries with it the memory of the moment it was emitted. To know whether someone else could already know us, we must trace those memories outward and ask which stars fall inside the circle of our past. The geometry is simple and inexorable. A signal launched in the year 1925 travels outward at the speed of light and sits today on a sphere whose radius equals the number of years since 1925. Anything inside that sphere can, in principle, receive that signal. Anything outside cannot be reached by it yet. Time becomes distance, and distance becomes history. Human radio leakage began in earnest a little over 100 years ago. That means our 20th century chatter has reached a sphere whose radius is approximately 100 light years. The exact boundary shifts slightly depending on which early transmissions one counts, but the order of magnitude is clear. Within that sphere are many thousands of stars, a neighborhood rich enough that the chance some host watchers is not negligible. To a civilization living around a star 30 light years away, the first crackles of our broadcasts are merely arriving now. To one at 50 light years, they see us as we were in the middle of the 20th century. The further out you go, the earlier in our history you encounter us. At 100 light years, the picture is of our first burst of technological noise, not our present. This moving shell imposes a strict constraint on who could possibly have heard us. There is a hard cutoff in causal contact. No civilization beyond the light years equal to our signal age can have been affected by that signal. They may be able to infer that an inhabited planet exists where our photons originated, but they cannot yet know anything that occurred after the date of the emissions they have received. The implication is a striking one. Any alien civilization that knows of our radio age lives, in their knowledge, in our past. They cannot be watching our present until light from our present reaches them. In cosmic terms, we are all historians, not contemporaries. This time delay complicates every danger narrative and every hope for real-time contact. If a nearby civilization at 15 light-years decided to reply the instant it detected our 20th century signals, its message would take 15 years to reach us. Our reply would take another 15 years to return. Exchanges across interstellar space are dialogues stretched into decades. Most of the drama we imagine, the rapid arrival of visitors, simply violates the physics of light speed. Exceptionally fast travel and communication are the speculative realm. Within the bounds of ordinary physics, the universe enforces patience. Distance also filters the kind of information available to a distant watcher. Biosignatures such as oxygen and methane imprint themselves on a planet's spectrum over geological timescales. The rise of oxygen in Earth's atmosphere during the Great Oxygenation Event occurred roughly 2.4 billion years ago. That signature has been visible to any sufficiently sensitive spectrograph in many directions for a very long time. It is the ancient shout of life. By contrast, technosignatures produced by industry are brief flickers in geological time. Carbon dioxide concentration rose markedly in the last 2 centuries, and synthetic compounds like chlorofluorocarbons appeared only in the last century. These industrial fingerprints reside nearer the outer edge of our radio bubble, and their detectability requires instruments far more powerful than those needed to find oxygen. For a distant civilization to know not just that Earth is alive, but that it has entered an industrial phase, they must either be close enough that our recent photons have reached them, or possess observational power vastly superior to ours. Proximity matters in other practical ways. The angular resolution necessary to map city lights or seasonal agriculture on a planet scales inversely with distance. To resolve the pattern of lights on the night side of Earth from a distant star requires telescopes with apertures or baselines so large as to stretch imagination if not physics. For a watcher within a few dozen light-years, a patient instrument could, over decades, assemble enough photons to make out large-scale patterns. At distances of hundreds or thousands of light-years, the faint smudge of a life-bearing world merges into the glow of its star and yields only coarse spectral data. Thus, the civilizations most likely to know intimate details about our geography and industry are those that are relatively nearby. The distant observers may know we were alive and industrial once, but not the texture of our cities. Another temporal twist arises from the variability of our own signals. Human radio and television leakage rose rapidly during the mid-20th century and then began to change as technology shifted. The transition from wide broadcast carriers to narrow digital beams and from over-the-air broadcasting to cable and fiber has reduced some forms of leakage. That means the window during which Earth is a conspicuous radio source may be quite brief on astronomical timescales. Civilizations that began listening only after that window closed might still see our biosignatures but miss our noisy technological adolescence entirely. The picture of detectability thus becomes a slender overlap of listener patience, listener sensitivity, and the briefness of our emission era. Consider the population of potential watchers inside the bubble. Stars of different ages and types occupy that volume. Some host long-lived planetary systems, where life may have had time to arise. Others are youthful and barren. The probability that a star hosts an intelligent civilization at the right technological stage to detect us is the product of many uncertainties. The Drake-style factors multiply into a vanishingly small number if any one of the steps is rare. That is the heart of the paradox. The sphere of our emissions may contain thousands of stars, but the fraction that host life and intelligent observers is unknown and could be tiny. Even an abundant galaxy may leave us effectively isolated by sheer improbability. There is also the issue of relative time. Civilizations have finite lifetimes, at least in the most plausible models. If technological civilizations tend to collapse or change on timescales shorter than the light travel delay to many neighbors, then contemporaneity becomes unlikely. A civilization that rose and vanished 300 years ago leaves no active listeners today at distances greater than 300 light-years. In this sense, the galaxy may be full of echoes from past ages rather than living audiences. The only civilizations capable of noticing us now are those whose lifespans overlap the window set by our emissions. That constraint favors neighbors near enough that communication delays are not overwhelming. The geometry of the light cone also allows an unsettling counterintuitive scenario. A civilization very far away could already know of an ancient Earth long before we could ever be aware of them. They might be watching eras of our planet that are now geologically distant and culturally irrelevant to us. They could catalogue the rise of life, the spread of oxygen, the emergence of multicellular organisms, and conclude that Earth was once teeming with simple life long before any technological species. Their records would be impressive, but their relevance to our present, minimal. The only watchers whose knowledge could shape our future are those whose view extends into our recent past, and who are near enough to act within timescales meaningful to us. Putting these pieces together yields a sober verdict. The set of civilizations that could already know of us in a way that matters to our present is limited by geometry, by the brevity of our technological glow, and by the unknown probabilities of life and intelligence. Many stars sit inside our expanding shell. Only a fraction could host watchers. With the combination of sensitivity, longevity, and proximity required to see the kind of detail that would change their behavior or ours. The rest may know of our existence as an ancient fact, not as a living reality. Thus, the cosmic truth stands clear and indifferent. The light that carries our presence travels outward and writes our history on the sky. Who reads it, when they read it, and what they do with that knowledge depends on where they sit in space and time. The map of possible watchers is a map of eras, not merely of stars. To know who could already know us, we must reckon with that map and accept that in the galaxy, timing is as decisive as distance. The scale of this light cone is difficult to grasp without slowing down to imagine it. Picture a sphere centered on the sun, 100 light-years in radius, filled with the faint wash of our earliest broadcasts. Within that space are more than 14,000 stars visible to the naked eye, and countless dimmer ones catalogued only by telescopes. Many are solitary suns like ours. Others are binaries or trinaries, dancing in gravitational embrace. A fraction of them host planets, and a smaller fraction host planets in habitable zones. Some of those planets may already have been watched for millennia by their own astronomers. To anyone living on such a world, a sudden appearance as a noisy neighbor would be an event of cosmic significance, however faint the whisper. The sheer variety of stars in this volume adds texture to the question of who could know us. Red dwarfs dominate by number, small and dim, but incredibly long-lived. Any civilization around them could persist for trillions of years if they survived their own adolescence. Yellow stars like our sun are fewer, but their luminosity makes them prime candidates for Earth-like worlds. White dwarfs, remnants of once vibrant stars, may also host planets or debris disks. All these types fall within our bubble, and each represents a different stage of stellar and planetary evolution. The odds of intelligence arising in any one system remain unknown, but the diversity ensures that if intelligence is common at all, some examples should already be within range of our signals. One must also account for the age of those stars. Many are far older than the Sun, giving any life on their planets a head start of billions of years. Others are younger, still unstable, unlikely to host advanced cultures. This temporal distribution matters. A civilization with a billion-year lead on us may have developed technologies that make our emissions trivial to detect, perhaps even from distances beyond the current light cone. But they would still be bound by physics. No signal travels faster than light. Even with perfect instruments, their knowledge of Earth is anchored to the photons that left us decades or centuries ago. They may be vastly older, but their view is still of our past. When we turn the problem around, we see how it constrains them as well as us. Suppose a civilization 50 light-years away detected our mid-20th century broadcasts. To act upon that knowledge, they would need to send a message or a probe. A radio reply would take 50 years to arrive. A physical probe, even traveling at a tenth of light speed, an immense technological achievement, would take 500 years. This means that if any watchers inside our light cone know of us, they may be planning or acting on information that is already outdated. Their intentions, friendly or hostile, cannot be informed by our present. They can only react to what they see, which is always history. The awareness of time delay brings with it an eerie sense of privacy and exposure combined. On the one hand, our present thoughts, inventions, and conflicts remain invisible to distant watchers. On the other, our past is laid bare without filter. Every clumsy, early broadcast, every spike of radar, every surge of carbon dioxide is recorded in the sky and cannot be recalled. Our past selves are transparent, while our present selves remain hidden until time delivers us to them. This paradox defines the nature of being known across interstellar space. It also reshapes the debate about whether aliens already know about us. If we mean, have they detected Earth as a living planet, then yes, that could have happened billions of years ago, when oxygen first transformed our sky. If we mean, have they detected us as a technological species, then the answer depends strictly on whether they are close enough to receive our last century of emissions. If we mean, do they know us as we are today, with our current technologies and crises, then the answer is no, unless they are within only a few light years, which dramatically narrows the set of candidates. Each version of the question yields a different set of watchers, separated not only by space, but by time, and so the narrative pushes forward. The universe is full of potential observers, but their knowledge of us is always delayed, fragmented, and filtered. They may already know we exist, but they cannot yet know what we have become. To accept this is to recognize a humbling boundary. Knowledge does not equal contact. Awareness does not equal influence. A civilization may have seen our signals and filed us away in their records, but that does not mean they are acting upon that knowledge. The constraint of distance ensures that knowledge alone is insufficient to produce contact. This realization leads to the next question. If some civilizations could already know, why have none revealed themselves? If awareness does not imply intervention, then perhaps the answer lies not in physics, but in choice. They may watch silently, or they may deliberately hide. The universe may not be silent by accident, but by design. And that design, whether ethical or strategic, is the focus of what follows. The map of our light cone, traced carefully across the stars, shows us who could know and when they could know. But it does not answer the deeper question of what they would choose to do with that knowledge. To understand this, we must think of the different layers of information that have been available across time. For most of Earth's history, long before humans emerged, the only signals leaving the planet were biological. The oxygen rise 2 billion years ago, the steady methane cycles, the seasonal greening of vegetation, all of these could have been measured by instruments as simple as spectrographs orbiting other suns. If advanced civilizations were already watching the galaxy back then, they would have seen Earth transform from a barren rock into a breathing biosphere. They would have known of life, but not of intelligence. For ages, we were only a blue-green anomaly, a quiet biological planet. That picture shifted abruptly when we began to radiate technosignatures. In the 20th century, our leakage was a sudden and unmistakable burst of structured noise. This moment in cosmic history is so brief that it looks like a flash, a signal that a biological planet has entered its technological adolescence. To a patient watcher, this transition is perhaps the most dramatic stage of any world's history, for it marks the threshold between a silent biosphere and a civilization capable of reshaping itself or destroying itself. To catch a planet in this stage is rare, because the window is narrow. Earth is now within it, and the photons of that transition have already reached dozens of nearby stars. Those are the civilizations that could already know of our arrival as a technological force. But the selectivity of time creates blind spots as well. Civilizations farther than 100 light years see only our pre-industrial past. To them, Earth remains a planet with life, but without intelligence. They may have catalogued us as an oxygen world rich in biology, unaware that a species now fills its sky with machines. Conversely, civilizations much closer than 100 light-years might know far more than we realize. They may already have logged the decline of our analog broadcasts, the rise of digital compression, the faint reduction in radio leakage as we moved into a quieter age. Their knowledge of us may extend into our late 20th century, only decades behind our present. Those who live still closer, within 20 light-years, have already seen our first space launches. The landing on the moon, the Cold War tensions, the fall of empires. They are watching our adolescence unfold in slow motion, as if through a glass darkly, but watching nonetheless. The emotional weight of this realization is profound. Somewhere out there, perhaps only 20 or 30 light-years away, there may be astronomers or machines who already know that a small planet, orbiting a yellow star, has become noisy. They might have records of our earliest voices, faint fragments of our old television shows, or the hum of our military radars. To them, we are not a mystery. We are a known fact. The only mystery is what we will become, and for that, they must wait as patiently as physics demands. This patience is central to the entire dilemma. Contact is not a moment, but a process stretched across decades and centuries. Even if a nearby civilization detected us the instant our first broadcasts reached them, the earliest possible response could not arrive for decades more. In the meantime, we continue to evolve, unseen. By the time any message or probe arrived, we would no longer be the same civilization that triggered their attention. They may address a humanity that no longer exists, speaking to a ghost of our past. From this perspective, the fact that no obvious signal has arrived yet is not surprising. The geometry of the light cone forbids it. If the nearest watcher is 30 light-years away, then our first broadcasts reached them only in the 1950s. A reply sent immediately would not arrive until the 2080s. Silence until then is not absence, it is simply the consequence of distance. The chapter therefore resolves into a paradox of knowledge. Many civilizations could already know of Earth, but what they know is partial and delayed. They may know we exist, they may know we became technological, but they cannot yet know what we are now. Their knowledge does not translate into immediate presence. Their awareness does not imply intervention. This distinction is critical. To imagine otherwise is to misread the physics of space and time. And so the stage is set for the next question. If aliens already know of us, and yet remain silent, perhaps the reason is not distance, but decision. Perhaps they have chosen to watch without revealing themselves. Perhaps they have embraced a principle of non-interference or a strategy of concealment. The silence may not be accidental but deliberate. To explore that possibility, we must turn to the ideas of quarantine, the zoo hypothesis, and the motives behind hiding. The silence of the stars presses against us like a weight. We know the galaxy should be full of worlds, and we suspect that some of those worlds must host life. Yet no signals have come, no visitors have landed, no unambiguous proof has appeared. This silence is not easily explained away. One answer is simply rarity. Perhaps intelligence is scarce, and we are among the first. But another possibility is more troubling and more subtle. Perhaps others are there, and they already know about us, but they choose not to speak. They watch, but they do not intervene. This is the essence of the zoo hypothesis, the idea that advanced civilizations may deliberately quarantine Earth, treating us as a protected reserve or a dangerous experiment. The metaphor of a zoo is not chosen lightly. On Earth, we sometimes keep species in enclosures, not to destroy them, but to observe them, to study their behavior, to preserve them for their own sake or for our curiosity. The animals inside may sense that they are being watched, but they do not control the terms of that observation. If aliens regard us in this way, then our place in the cosmos is humbling indeed. We would not be fellow participants in a galactic community, but specimens held at arm's length. The bars of the cage would not be iron, but ignorance, enforced by silence and concealment. To imagine such motives, we can look at the history of human behavior toward less technologically advanced cultures. At times we have sought to dominate and exploit, but at other times we have created reserves, attempted to protect, or enforced rules of non-contact. Anthropologists debate the ethics of observing without interfering, knowing that even observation itself can change what is observed. If a civilization has survived long enough to reach the stars, perhaps it has embraced an ethic of non-interference, recognizing the dangers of cultural contamination. From their perspective, premature contact could distort our development, erase our traditions, or overwhelm us with knowledge we are not ready to bear. But ethics may not be the only reason to hide. There may be practical or strategic motives. By remaining silent, they avoid revealing their own presence to civilizations that might be hostile. By cloaking their observation, they maintain the ability to act without being seen. Even if they wish us no harm, prudence may dictate caution. A galaxy of watchers may agree, implicitly or explicitly, that silence is the safest policy. Earth is not ignored but deliberately isolated, its broadcasts noted but not answered, its signals catalogued but not acknowledged. We live inside a kind of quarantine bubble, not because we are unworthy of contact, but because silence serves a larger strategy of survival. Could such hiding be achieved in practice? The first layer is simple: do nothing. Receive our signals, record them, but never transmit in return. From our perspective, the sky remains silent. The second layer is more speculative: active concealment. In principle, a sufficiently advanced civilization could attempt to block or absorb Earth's signals, cloaking us from detection by others. The energy requirements are immense, but not impossible to imagine. A swarm of satellites could intercept and scatter our radio leakage, or a cloud of engineered dust could dim our spectral signature. To us, the sky would appear unchanged, but to the galaxy, we would be invisible. Whether such measures are plausible or necessary is another matter, but the concept itself cannot be dismissed outright. The possibility that Earth is cloaked by design is unsettling. It suggests that someone, somewhere, has already made a decision about our fate. It suggests that the silence of the stars is not the result of emptiness, but of policy. If the galaxy is full of civilizations, and all have agreed to remain silent to young species, then the zoo is not a metaphor, but a reality. We are inside it, unaware of its walls, wondering why no one answers. The problem with this hypothesis is that it is difficult to test. Silence looks the same, whether it is natural or deliberate. The absence of evidence is not evidence of absence, but neither is it proof of concealment. We are left with philosophy as much as science, asking what motives would be necessary for such a system to exist. Would civilizations independently choose silence, or would they need to coordinate? Could there be a galactic code, an unspoken law, that forbids interference with emerging species? If so, who enforces it, and why? The zoo and quarantine hypotheses do not explain everything, but they offer a lens through which silence acquires meaning. If they already know about us, their silence may not be a void, but a choice. The watchers may be waiting, testing whether we can mature on our own, refusing to intervene until we demonstrate readiness. To some, this idea is comforting. To others, it is chilling. But either way, it shifts the burden of explanation from physics to intention. And it raises the next question. If they are hiding, if they are watching, without revealing themselves, then some kind of infrastructure must exist. Cloaking, surveillance, or quiet monitoring all require systems, machines, stations, or probes positioned in space. What would such a monitoring system look like? Where would it be placed, and why have we not found it? That puzzle takes us from motive back to method, and it is the path we must now follow. If the silence of the galaxy is not emptiness but choice, then the choice itself must leave traces. Hiding requires infrastructure. Even the most subtle act of concealment is still an act, and acts require tools. To cloak Earth, to monitor us without revealing themselves, to enforce a quarantine, or maintain a zoo, someone somewhere must be operating systems of immense power. The paradox is that these systems, by design, are invisible to us. Yet by reasoning through what they would need, we can sketch the outlines, of what might exist beyond our sight. Start with the simplest scenario, passive observation. The easiest way to hide is to do nothing except watch. A civilization could build enormous arrays of telescopes in their own star system, tuned to detect our every signal. To us, they would remain undetectable, as nothing travels outward from their instruments. The only evidence of their attention would be silence. Such a setup would be the minimal infrastructure of a zoo hypothesis, a network of watchers that never transmits, never interferes, but notes everything. It requires no cloaking technology, no presence in our solar system, only patience and restraint. The next step is more active concealment. Imagine that our broadcasts, rushing outward, are intercepted by a fleet of satellites positioned in deep space. These machines could absorb or scatter the signals, preventing them from traveling farther. They might operate in a spherical shell around Earth, or as a directional shield oriented towards certain regions of the galaxy. The scale of such an undertaking is beyond our current capabilities, but not beyond imagination. A civilization that builds megastructures, that harnesses energy on the scale of stars, could maintain such a cloak with ease. To us, it would be invisible. To the rest of the galaxy, Earth would appear silent. A still stranger possibility is manipulation of our spectral fingerprint. Our atmosphere glows with signs of life and industry. Oxygen, ozone, methane, carbon dioxide, chlorofluorocarbons. These are the kinds of signals our own astronomers search for in exoplanet surveys. If a civilization wished to hide us, they could, in principle, mask those signatures by placing absorbing or scattering material between Earth and distant observers. A carefully engineered cloud in high orbit, or an array of machines positioned at the right distance, could cancel the spectral lines or mimic a lifeless world. The physics of such cancellation is demanding, but not inconceivable for a species far older than us. The energy cost would be enormous, but energy may be abundant to those who command stellar resources. There is also the notion of selective hiding. Instead of cloaking Earth from the entire galaxy, they might shield us only from particular directions. If they fear the attention of a hostile empire in a certain region, they could build directional masks to keep us hidden from that quarter. From other angles, Earth might still be visible. This selectivity introduces a complication. Whether Earth appears silent depends not only on us, but on where the observer sits. The zoo may not be uniform. Some neighbors may see us, others may not, depending on who the wardens of the quarantine choose to block. If quarantine is real, it is likely coordinated. A single civilization acting alone cannot hide an entire planet from all observers. It would require either a galactic scale policy or at least cooperation among a network of advanced species. This is where the hypothesis stretches thin, for coordination on such scales demands a stability and trust we can hardly imagine. Yet, it is not impossible. Humans have created international treaties banning certain weapons and protecting certain habitats. Perhaps older civilizations, after surviving the dangers of adolescence, recognized the risks of premature contact and agreed to enforce silence across the stars. To us, it looks like emptiness. To them, it is law. The infrastructure of hiding may not be entirely external. There are darker scenarios in which probes within our own system serve to suppress signals or intercept transmissions. A probe stationed at a stable point could transmit counterwaves, cancelling our emissions in targeted bands. Another could monitor us directly, ensuring that nothing escapes unrecorded. Such devices, if small and cleverly hidden, might escape our detection indefinitely. Our surveys of near-Earth space are incomplete. Our mapping of the lunar far side is still imperfect. Our ability to detect objects in the outer solar system is far from comprehensive. In these gaps, concealment could lurk. Yet we must temper speculation with skepticism. The energy costs of cloaking an entire planet are extreme. The coordination required to enforce a galactic silence is immense. The very idea risks becoming unfalsifiable. Silence can always be explained as deliberate. The zoo hypothesis is compelling, but its strength is also its weakness. It explains too much with too little evidence. The challenge is to ask whether it is the simplest explanation or whether silence is better explained by scarcity, distance, or chance. Still, the exercise is valuable. By imagining what it would take to hide us, we sharpen our sense of what it would mean if aliens already know about us but remain silent. If the zoo is real, then we are not alone. We are surrounded by watchers who enforce a quarantine. If it is not real, then silence may be emptiness after all. In either case, the question that follows is practical. If there is infrastructure of observation or concealment, could we detect it? Could we search for probes, for anomalies in our sky, for signatures of interference? This leads us to the frontier of speculation where science meets imagination, the search for probes and artifacts left behind by those who watch. If there is a quarantine, then its presence is both protective and isolating. To imagine ourselves inside such a construct is to imagine a paradoxical existence. We are important enough to be watched, but not significant enough to be spoken to. We are alive in a galaxy where others may already know of us, yet we remain cut off by design. The silence is no longer neutral background. It becomes intentional, a choice imposed upon us. That idea alone reshapes how we think about the night sky. Every star could conceal not only neighbors but wardens. Consider how such a quarantine might feel from within. We look out and see a quiet universe, empty of signals. Conclude, we may be alone. That conclusion shapes our culture, our philosophy, and even our policy. But if silence is imposed, then our worldview is being guided without our consent. The very absence of evidence is itself evidence of manipulation. To those on the outside, this may appear benign, even compassionate. They might argue that a young civilization must grow on its own before it can meet others. But to those on the inside, it is indistinguishable from neglect. We may be prisoners in a cage we cannot see, told only by our own ignorance that we are free. The zoo metaphor has limits, and some thinkers prefer the word quarantine. A zoo suggests entertainment, that we are watched for curiosity or amusement. A quarantine suggests danger, that we may spread infection or cause harm. Perhaps the silence is not to protect us, but to protect them. From their perspective, a violent and unpredictable species, broadcasting its presence, could be a risk. Containing that risk, by muting our signals, may be an act of defense rather than mercy. In this darker scenario, Earth is not a reserve but a holding pen, kept isolated until its inhabitants either destroy themselves or prove they can be trusted. The feasibility of such control is debatable. Cloaking every emission, masking every spectral line, intercepting every probe, these tasks require technology beyond anything we can presently imagine. Yet to civilizations millions of years older, the challenge may be trivial. For them, the manipulation of planetary signatures could be as routine as weather control is becoming for us. The energy requirements, while vast, are not unthinkable for a culture that harnesses the output of a star. We must be careful not to mistake our limitations for universal laws. Still, skepticism is necessary. The simplest explanation for silence remains that civilizations are rare, scattered, or short-lived. The zoo hypothesis is not proven by the absence of evidence. It is one interpretation among many. To treat it as certainty is to fall into a trap of anthropocentric projection, imagining that aliens would behave as we do when faced with less advanced species. We do not know if they would choose non-interference. We do not know if they would care enough to cloak us. But the hypothesis is compelling because it accounts for the one fact we cannot deny. The silence is louder than it should be. Whether zoo or quarantine, the implication is that some form of infrastructure must exist. There must be monitoring stations, probes, or networks designed to enforce the silence. If so, then traces of them might be within reach. Perhaps hidden on the far side of the moon, perhaps stationed at stable gravitational points, perhaps drifting in the asteroid belt. If the silence is deliberate, then evidence of the silencers could be closer than we think. That possibility shifts the focus from abstract speculation to concrete search. Instead of only listening for distant signals, we might look for nearby artifacts, And so the path leads naturally from the philosophy of quarantine to the practicality of probes. If aliens already know about us and have chosen to remain silent, the instruments of that silence may be hiding in plain sight. The absence of detected probes is itself mysterious, and exploring that mystery is the next step. The zoo and quarantine hypotheses ask why. The search for probes asks how. Together they form the bridge to the next chapter, where the silent visitors of possibility take center stage. The zoo and quarantine ideas imply that if others already know about us, then there must be systems in place to keep watch. Remote telescopes across light years are one option, but probes placed within our own solar system are another, and in many ways, they are the most direct. The concept of an alien probe lingering nearby is not fantasy dreamed up by modern science fiction, but a suggestion put forward seriously by scientists themselves. In the 1960s, Ronald Bracewell proposed that an advanced civilization might send autonomous machines, now called Bracewell probes, to serve as messengers and observers. Unlike fragile radio signals, a probe can wait, adapt, and respond. It can bridge the gulf of light-speed delay by being present when the civilization it monitors becomes ready to engage. Imagine what such a probe would look like if it existed in our solar system. It would not be a gleaming saucer or a dramatic monolith standing in plain view. More likely, it would be small, stealthy, engineered to blend with natural bodies. It might hide among the asteroids, disguised as a rock, its sensors peering outward with patience. It might orbit in the shadow of the moon, where human eyes seldom linger. It might rest on the far side of a comet, shielded until the time comes to reveal itself. The key principle is longevity. A probe meant to monitor a young civilization must endure not just years, but centuries or even millennia. That requires designs beyond our current abilities, but not beyond imagination, self-repairing mechanisms, hibernation modes, energy harvesting from solar radiation, or planetary magnetic fields. The solar system offers many natural hiding places. The Earth-Sun Lagrange points are stable regions where gravity and orbital motion balance perfectly. Spacecraft placed there require little fuel to stay put, and they have wide views of Earth and its orbital neighborhood. A probe at the Earth-Sun Lagrange point 2, a million miles beyond Earth, could quietly observe our planet with perfect vantage and remain unnoticed amid the clutter of natural space debris. The lunar far side offers another sanctuary, eternally shielded from Earth's radio chatter, making it a prime location for eavesdropping devices. Even the asteroid belt is a candidate. With hundreds of thousands of irregular bodies, a small probe tucked among them could avoid detection indefinitely. Searches for such artifacts have been attempted, though rarely with systematic rigor. Astronomers have scanned the moon for unusual reflectivity, mapped near-Earth asteroids, and considered proposals for targeted surveys. So far, nothing unambiguous has appeared. Skeptics argue that absence of evidence means absence of probes. Others counter that our searches have been shallow, our data incomplete, and our expectations naive. A probe designed to remain hidden would not glow brightly or transmit continuously. It would mask its signature, blending into noise, waiting silently until a trigger event, perhaps the detection of our first interstellar probe, or a deliberate transmission activated it. The absence of detection may say more about our limited efforts than about their absence. The concept of a Bracewell probe also resolves some paradoxes of interstellar communication. Radio signals suffer from time delay and require ongoing transmission. A probe sent once can last for ages, needing no further attention from its creators. It can make its own decisions, adapt to the local context, and interact with us in ways a distant civilization cannot. For a culture with patience, probes may be the most efficient means of contact. Indeed, if we one day discover signs of a young civilization orbiting a nearby star, sending a probe may be our own best strategy, rather than shouting across the light years with fragile radio waves. There are darker interpretations as well. Probes need not be friendly observers. They could serve as surveillance devices, tracking our military progress, cataloging our resources, or even enforcing a quarantine by disabling transmissions that attempt to leave the planet. A sufficiently advanced probe might even have defensive or offensive capabilities, preventing us from reaching beyond our system until the time is judged right. While this may sound like science fiction, it is a possibility that follows logically from the zoo or quarantine hypotheses. If Earth is under observation, the tools of that observation may not be passive. They may be guardians or wardens, whether benevolent or not. The resilience of probes on cosmic timescales is another challenge. Space is harsh. Radiation, micrometeoroids, and thermal extremes erode any material. Yet we ourselves already design spacecraft that can last for decades, and with self-repair and redundancy, centuries may not be impossible. A civilization millions of years ahead could engineer machines built to endure longer than the age of our species. Self-replicating probes, sometimes called von Neumann machines, extend this endurance still further. Such a machine could land on asteroids or moons, harvest raw materials, and build copies of itself, replacing losses and spreading across the solar system. The result would be an invisible web of watchers, each maintaining the presence of its kind indefinitely. The unsettling thought is that if such probes exist, they may already have been here for longer than human history. They may have arrived when Earth first showed signs of life, billions of years ago, and waited through the ages until intelligence appeared. To them, our entire history would be a brief flicker. They may have seen the rise and fall of civilizations long before we wrote history. They may have archived every signal we ever emitted. If they are silent, it is not because they cannot speak, but because they will not, at least not yet. So far, we have found nothing conclusive. But absence of evidence is not proof of absence. We have barely begun to search systematically for artifacts in our own solar system. Our telescopes glance past asteroids. Our lunar maps are still incomplete. Our radar sweeps are selective. If probes hide here, we may simply have overlooked them. The possibility remains open, and the logic behind it is strong enough that it cannot be dismissed lightly. The thought leads to a sharper paradox. If probes are the natural means of observation, and if advanced civilizations are common, then why have we not found any? Why is the solar system not littered with artifacts? Why do we not see even a trace of such machines? Absence itself becomes data. It forces us to confront the possibility that we are alone, or that civilizations rarely send probes, or that probes exist, but are deliberately concealed. Whatever the explanation, the silence of artifacts mirrors the silence of signals. We are caught again between emptiness and concealment, between rarity and restraint, and that tension propels us toward the next question. The absence of detected probes is not neutral, it is part of the wider silence. To understand what it means, we must revisit the Fermi paradox itself. If aliens already know about us, and if probes or signals are the natural way to show it, why is everything still so quiet? The next chapter returns to that question with renewed force, weighing evidence against silence and possibility against probability. If probes are a natural strategy for advanced civilizations, then we must wrestle with the mechanics of how such machines could survive for ages and what traces they might leave behind. A probe launched across interstellar distances must endure not just years but centuries or millennia of exposure to the void. Radiation, collisions with dust grains, and the stresses of acceleration all threaten to tear it apart. Yet, we ourselves are beginning to solve such problems on a smaller scale. Our Voyager spacecraft, though fragile by comparison, continue to function more than 40 years after launch. Extrapolate that capacity forward by a few centuries of technological progress, and the idea of a probe built to last tens of thousands of years is not far-fetched. One strategy for endurance is redundancy. A probe may be packed with multiple systems, each capable of taking over if one fails. Another is hibernation. The machine might spend most of its journey in a dormant state, waking only at intervals or upon arrival. This saves energy and slows wear. Energy itself may come from solar power, nuclear decay, or even exotic mechanisms we cannot yet command. To an advanced builder, these are engineering puzzles. not impossibilities. A probe need not be large. It could be as small as a human satellite, yet packed with sophisticated sensors, communication systems, and self-repairing nanotechnology. The question of survivability also raises the idea of replication. Von Neumann probes, as theorized by mathematician John von Neumann, would not only travel, but reproduce. Upon reaching a new system, such a probe could mine local resources, construct a copy of itself, and send that copy onward. Over millions of years, a single seed probe could spread across the entire galaxy, populating it with observers. The replication process would allow indefinite endurance, since damaged probes could be replaced by new ones. Critics worry about runaway replication, machines devouring resources uncontrollably, but careful design might prevent that. If the concept is feasible at all, then the galaxy should already be filled with such machines, unless civilizations choose not to build them. The absence of visible probes in our own solar system is therefore puzzling. If replication is efficient and common, we should see evidence of it everywhere. Some argue that the absence is proof that civilizations are rare or short-lived, that few survive long enough to spread their machines. Others suggest that probes exist, but are designed for stealth. If their mission is observation without interference, then they would hide carefully, mimicking natural rocks, keeping power levels low, and transmitting only in narrow beams, invisible to us. To find them would require deliberate searching with instruments tuned to look for anomalies, not broad surveys designed for other purposes. There have been tentative attempts. Radar surveys of near-Earth asteroids have revealed curious shapes, but nothing clearly artificial. High-resolution imaging of the lunar surface has mapped old spacecraft from human missions, but no alien artifacts. Proposals have been made to search systematically for probes in stable gravitational points, to analyze anomalies in orbital debris, or to scan the lunar far side. With care, none of these has yet been carried out with the rigor required to rule out their presence. Our attention remains focused outward, listening to distant stars, while the possibility of close observers remains underexplored. Speculation about probe behavior also extends beyond observation. What if probes are not only watching, but waiting to act? They might be programmed to respond to triggers. The first nuclear explosion, the first interstellar probe launched, the first deliberate message sent. Their silence could be conditional, waiting for signs of maturity. Alternatively, they might serve as guardians, preventing us from broadcasting too widely until we are judged ready. Science fiction imagines probes that intervene to disable dangerous technology. But even without fiction, the idea of conditional response fits the logic of a quarantine. A probe can be silent for centuries, then activate when its rules are met. The psychological impact of such a discovery would be enormous. Imagine if tomorrow astronomers announced they had found a small object at a Lagrange point, not a natural asteroid, but a machine of non-human origin. The debates of the last century would collapse overnight. We would know beyond doubt that we are not alone, and that we have been under observation for an unknown length of time. The political and cultural consequences would ripple across the planet. Every decision about space exploration, communication, and defense would be reframed. And yet, even with proof in hand, we would still not know the motives of the watchers. Discovery would end one mystery, but deepen another. Skeptics remind us to be cautious. The absence of clear evidence, despite decades of astronomical data, suggests that if probes exist, they are rare or expertly hidden. Many anomalies once hailed as possible artifacts, odd signals, unexplained objects, have turned out to be natural phenomena. The burden of proof for such an extraordinary claim is immense. Without direct detection, probes remain speculation. Still, the plausibility of the idea, its grounding in both logic and engineering, keeps it alive. Scientists continue to propose searches not because they expect certain discovery, but because the possibility is too important to ignore. The paradox grows sharper. If probes are the natural solution to interstellar monitoring, and if civilizations are common, then we should see them. We do not. Either civilizations are rare, or probes are hidden, or their missions ended long ago. Each answer reshapes our understanding of who might already know about us. If no probes exist, then perhaps no one is watching closely. If probes are hidden, then we may be under observation, without realizing it. If probes once existed but have fallen silent, then perhaps civilizations come and go, leaving relics in their wake. This tension drives us back to the same question that haunts all of these discussions: the silence. We see no signals. We find no artifacts. We uncover no probes. Either the galaxy is quieter than we expect, or it is filled with voices that choose not to speak. The next part of this chapter must confront that paradox directly, asking what the absence of probes means, and whether silence itself can serve as evidence. If the possibility of alien probes stirs our imagination, the stubborn absence of any evidence forces us into paradox. For decades, humans have been mapping the solar system with ever sharper eyes. We have charted the surface of the moon in detail, surveyed Mars from orbit, and with rovers, probed the outer planets, and tracked thousands of asteroids. In all of this, nothing has appeared that unambiguously points to an artifact of non-human origin. There are strange rocks and peculiar signals, yes, but every candidate so far has yielded to natural explanation. If probes are the obvious solution for monitoring young civilizations, then why is the solar system silent of them? One answer is that probes are indeed here, but they are designed to remain hidden. A machine meant to watch without revealing itself could be the size of a refrigerator, a car, or even smaller. It could mask its heat signature, match the albedo of a rock, and remain dark until activated. We rarely scrutinize every asteroid with the precision required to detect such camouflage. Even our surveys of orbital debris around Earth are incomplete, and those objects are in our immediate neighborhood. Extend the search to the asteroid belt, the Kuiper belt, or the distant Oort cloud, and the volume is so vast that 1,000 probes could hide without notice. Concealment is not difficult when the searcher is inattentive. Another answer is that probes were once here, but they are gone. Civilizations may send observers only during a brief window, then recall them, or allow them to decay. Machines can fail. A probe designed to last 100,000 years may still eventually fall silent. If Earth has been interesting for billions of years, then many probes may have come and gone in that time, leaving no trace. Our own probes, like Voyager, will drift silently through space long after they fail, unremarked by anyone who passes near them. To discover a relic of such a mission would be extraordinary, but the odds of stumbling upon one are slim, unless we know exactly where to look. The third answer is starker. Perhaps civilizations are rare, and probes never came because there were none to send them. The silence we encounter may not be policy or concealment, but simple scarcity. If life is rare, if intelligence is rarer, and if technological civilizations survive only briefly, then perhaps Earth is one of very few places to emerge into awareness. In such a galaxy, the absence of probes is natural. We may be alone, or nearly so. To us, this is a bleak interpretation, but it is consistent with the evidence we actually have. Still, the logic of probes continues to haunt us. For a civilization interested in efficiency, sending a probe is rational. It avoids the limitations of radio, it allows flexible interaction, and it ensures that knowledge can be updated in real time. It is, in many ways, the solution we ourselves might choose if we detected a young civilization within a few dozen light years. That is why the absence troubles us so deeply. It suggests a gap between what we expect and what we see, a gap that cannot easily be closed. Some speculate that probes, if they exist, might operate under rules we cannot guess. Perhaps they are programmed not to reveal themselves until we reach a certain threshold, like the colonization of our solar system or the launch of interstellar ships. Perhaps they are waiting for a deliberate signal, a kind of cosmic password. Until then, they remain silent, their presence masked by design. This conditional activation would explain why we have not found them, but it also means that discovery may depend on our own actions, not theirs. The zoo hypothesis returns here in mechanical form. The probe is the zookeeper, waiting to see whether the animals are ready for contact. The absence of detected probes thus becomes data of its own. It tells us either that the galaxy is more empty than we wish, or that it is more carefully managed than we suspect. Both possibilities are unsettling. Either we are alone in a silence imposed by chance, or we are surrounded by watchers whose silence is deliberate. In both cases, our place in the cosmos is uncertain, and our knowledge incomplete. This is where the probe question folds back into the larger riddle known as the Fermi paradox. If civilizations are common, and if probes are efficient, then where is everybody? Why is the solar system not filled with machines, signals, or relics? Why does the universe look empty when logic suggests it should be alive with watchers? The absence of probes is not a side detail. It is central to the paradox itself, and so the narrative turns once again from signals to motives, from motives to methods, from methods to probes, and now from probes back to silence. The silence is deeper than we expected, and more troubling than we admit. To confront it, we must revisit Fermi's haunting question: where is everybody? Under the assumption that at least some civilizations already know of us. That is the path of the next chapter, where evidence and absence must be weighed together in the harsh light of probability. The question is simple to ask and impossible to ignore. Where is everybody? Enrico Fermi posed it over lunch in 1950, and the paradox that bears his name has echoed through science and philosophy ever since. The galaxy is vast, its stars are ancient, and the conditions for life appear common. If civilizations arise with any frequency, then the sky should be filled with their signals, their probes, their artifacts. Yet when we look, we find nothing. No unambiguous transmission. No glittering machine in the asteroid belt. No trace of visitors past or present. Silence reigns, and the silence is deafening. The paradox sharpens when framed against what we have already explored. Earth has been broadcasting its presence for a century, perhaps more. Our signals now bathe thousands of stars within 100 light years. Our biosignatures have been visible for billions of years, proclaiming the presence of life to anyone with the instruments to look. If other civilizations exist, then they could already know about us. And yet, knowing or not, none has revealed itself. This is not just puzzling, it is deeply contradictory. Probability says they should be there. Observation says they are not. The space between those statements is the paradox. To tackle it, scientists often turn to the framework of the Drake equation, the rough attempt to estimate the number of communicating civilizations in the galaxy. The equation multiplies a series of factors: the rate of star formation, the fraction with planets, the number of habitable planets per system, the fraction that develop life, the fraction of life that develops intelligence, the fraction that becomes technological, and the lifespan of such civilizations. The early terms stars, planets, habitable zones are increasingly well constrained. Exoplanet surveys show that planets are common, and many orbit in regions where liquid water could exist. Life, then, should not be rare by conditions alone. The later terms, however, are murky. We know of only one example: ourselves. Whether life arises easily or rarely, whether intelligence is inevitable or exceptional, whether technology endures or collapses quickly, on these points, the data is zero. The result is uncertainty that spans orders of magnitude. Within that uncertainty lies the heart of the paradox. If the probabilities are generous, then the galaxy should be teeming with civilizations, many of them far older than ours. Given time, they should have spread, leaving probes or colonies scattered everywhere. Even a single replicating probe species could have filled the galaxy in a fraction of its age. If the probabilities are stingy, then perhaps we are alone, or nearly so. And silence is not paradox but reality. Which interpretation is correct is not obvious, but both clash with expectation. Abundance suggests presence we do not see. Scarcity suggests loneliness we cannot confirm. Adding to the puzzle is the fact that our searches, while limited, have not been entirely blind. Radio telescopes have scanned the skies for decades, listening for narrowband signals that would stand out from natural noise. Optical instruments have searched for laser pulses. Infrared surveys have looked for the waste heat of advanced industry. Spacecraft have mapped planets, moons, and asteroids in our own system. None of these efforts has found unambiguous evidence of alien activity. It is possible that we are looking in the wrong way, or that signals are encoded beyond our recognition. But the fact remains that the simplest forms of detection have so far failed. The universe, to the limits of our tools, looks quiet. This is where the idea that aliens already know about us complicates the paradox. If they are aware, then their silence cannot be explained by ignorance. It must be intentional, or at least circumstantial. Perhaps they are deliberately refraining from contact, choosing to let us develop undisturbed. Perhaps they are too distant to reach us in meaningful time, even though they see us. Perhaps they are so different in form or thought that what we take for silence is not silence at all, but communication in modes we cannot perceive. The paradox remains, but the possible explanations multiply. Some scientists argue that the silence is a selection effect. Civilizations that broadcast widely may expose themselves to danger and be eliminated. Those that survive may be precisely the ones that choose caution, who watch but do not speak. From this perspective, our own broadcasts may be a phase of adolescence, soon to end as we realize the risks of shouting into the dark. If this is true, then the silence is not surprising. It is the survival strategy of those who endure. The watchers already know of us, but they remain hidden because that is what survival demands. Others suggest that the filter lies in the future. The so-called Great Filter hypothesis posits that civilizations tend not to last, that something war, ecological collapse, technological catastrophe destroys most before they can spread or make themselves visible. If this filter is behind us, then we are rare survivors. If it is ahead of us, then our silence will one day be permanent too. In either case, the paradox is softened by tragedy. Civilizations vanish before they can fill the galaxy. The paradox also sharpens our awareness of time. The galaxy is billions of years old. Civilizations could have arisen millions of years before us. If even a handful survived and spread, their artifacts should be everywhere. The fact that they are not suggests either that spreading is far harder than we imagine, or that civilizations choose not to spread. Both explanations contradict human instinct, which assumes expansion is inevitable. Perhaps the flaw is in our projection, not in the galaxy. And so the Fermi paradox, when revisited through the lens of aliens who may already know us, does not shrink but deepens. Silence is no longer neutral. It becomes data that must be explained. Either the universe is empty, or it is full but quiet. Either probes never came, or they are here and hidden. Either civilizations vanish, or they choose restraint. In each case, the contradiction remains. Expectation collides with observation, and what emerges is mystery. What the paradox teaches, above all, is humility. Our sample size is one. Our searches are narrow. Our timelines are short. To demand an answer from so little evidence is to invite confusion. But the paradox also serves as a compass. It forces us to ask better questions, to refine our searches, to consider motives as well as mechanics. It reminds us that the absence of proof is not proof of absence, but neither is it meaningless. Silence itself is a phenomenon, and it may yet reveal as much as a signal. The paradox leads naturally to the next inquiry. If aliens already know us, and if their silence is deliberate, then what are the possible consequences for us? What risks do we face? What ethics are involved? And how should we respond if contact ever comes? The next chapter turns to those questions, exploring the politics of contact and the fragile choices that would shape humanity's future in a galaxy that may not be as empty as it seems. If the Fermi paradox is the silence of expectation unmet, then part 2 must wrestle with the spectrum of explanations that attempt to tame that silence. Each explanation is both a mirror of our assumptions and a test of our imagination. When scientists and philosophers list possibilities, they range from the most mundane to the most unsettling. but all circle the same reality. The galaxy should be alive with evidence, yet it is not. One family of answers points to scarcity. Perhaps life itself is rare, and Earth is an outlier. Despite the billions of planets orbiting billions of stars, the chemical steps that led from simple molecules to self-replicating life may be unlikely beyond measure. This explanation places the great filter at the very beginning, in the leap from chemistry to biology. In such a universe, silence is not surprising. We are alone because the odds were stacked against life from the start. To hold this view is to see ourselves as improbable survivors in a cosmos of sterile rocks and empty seas. Another explanation shifts the filter to the rise of intelligence. Life may be common, but intelligence may not. Dinosaurs ruled Earth for more than 100 million years, without producing technology. Even after humans evolved, for most of our history, we lived as toolmakers, but not world changers. If intelligence is not inevitable but rare, then the galaxy could teem with microbes, forests, and oceans, yet remain devoid of civilizations capable of radio, spacecraft, or probes. Silence in this scenario is not emptiness, but abundance without awareness. It is a galaxy, alive, but mute. A darker possibility lies in survival. Civilizations may arise often, but they may not last. The great filter, in this view, is still ahead of us. Perhaps every technological species eventually invents weapons it cannot control, exhausts its resources, or triggers environmental collapse. The silence is the graveyard of countless civilizations, each extinguished before it could spread. If this is true, then the absence of probes and signals is not mystery, but warning. Our future may be as fragile as theirs, our silence inevitable, unless we find a way to break the cycle. The zoo and quarantine hypotheses fit into another category: silence by choice. Here the galaxy is full of civilizations, but they have decided not to reveal themselves. They know of us but remain hidden, observing us like anthropologists, waiting for signs of readiness. This explanation fits our theme most directly. They already know, but their knowledge does not translate into communication. It requires not just scarcity or catastrophe, but intent. It paints the silence not as accident, but as policy. The paradox is also sharpened by the scale of time. The galaxy is older than Earth by billions of years. If even one civilization arose early and chose to expand, it would have had ample time to colonize every star. The absence of evidence suggests either that colonization does not happen or that expansion is not the universal instinct we assume. Perhaps civilizations find fulfillment inward, creating virtual worlds or harnessing their stars without venturing far. To them, spreading across the galaxy may be pointless. If so, then silence is not absence but self-containment. Critics of the paradox argue that our expectations may be flawed. We assume that alien communication will resemble ours, that their probes will look like machines we can imagine, that their motives will align with ours. But what if their physics is different, their cognition alien, their priorities beyond comprehension? What if they communicate through mediums we cannot detect, or operate at scales we cannot perceive? The silence we interpret as absence may be the buzzing of a network that we lack the senses to hear. The paradox, then, may be less about them and more about us. Still, even with humility, the silence feels too complete. No flicker of a Dyson sphere's waste heat, no steady beacon at obvious frequencies, no obvious artifacts drifting nearby. For all the explanations we invent, the data remains. The stars are quiet, and that quiet demands explanation because it is not what probability leads us to expect. The paradox, therefore, is not merely a philosophical puzzle but a scientific challenge. It forces us to refine our assumptions, expand our searches, and question the inevitability of our models. For those who hold that aliens already know about us, the paradox is even sharper. If they know, then the absence of action must mean something. It could mean disinterest, as if Earth is unremarkable among countless worlds. It could mean caution, a deliberate choice to avoid cultural contamination. It could mean strategy, silence as survival. Or it could mean that what they know about us is less than we imagine, limited by distance, delay, or interpretation. They may know that Earth has life, but not that humanity has reached its technological adolescence. They may know we exist, but not who we are. The weight of these possibilities leads to a sobering conclusion. The Fermi paradox is not likely to yield a single neat solution. The galaxy may contain a mixture of answers, some civilizations rare, some short-lived, some silent by choice, some invisible to us. The paradox endures because it reflects a clash between expectation and evidence, not because it has a hidden key waiting to be found. What it reveals most is the limits of our own perspective, the narrowness of our knowledge, and the vastness of the unknown. And yet the paradox is not just an intellectual exercise. It carries consequences for how we act. If silence means rarity, then our responsibility is immense, for we may be one of the few aware species in the galaxy. If silence means danger, then caution is wise, for reckless broadcasting may expose us to risks we do not understand. If silence means choice, then our challenge is to demonstrate readiness, to show that we can mature without destroying ourselves. In all cases, the paradox is a call to humility and prudence. The next part of this chapter must weigh these consequences in sharper focus. Silence is not neutral. It carries risks, implications, and demands. If aliens already know of us, what might their continued silence mean for our future? What should we learn from the paradox, and how should we act in response? The paradox, when stretched to its furthest edges, becomes more than a riddle of numbers and probabilities. It becomes a mirror held up to humanity itself. We look outward and wonder why the galaxy is silent, but in doing so, we reveal our own expectations, our fears, and our instincts. The silence is not empty of meaning. It forces us to confront the possibility that our place in the cosmos is precarious, and that how we interpret the quiet sky may shape our destiny. Consider again the assumption that civilizations expand. It is rooted in our history. When humans find new land, they explore it, exploit it, and colonize it. We expect others to do the same. But what if expansion is not universal? What if most civilizations turn inward, seeking fulfillment in digital realms, in artificial realities, or in carefully balanced ecologies around their own stars? They may see galactic expansion not as triumph, but as folly, waste, or even danger. If that is the case, then the silence is not paradoxical at all. It is simply the sound of civilizations choosing paths different from our own. Now consider the possibility that civilizations do expand, but with subtlety. They may seed probes across the galaxy, each designed to hide until conditions are right. We would see nothing until we cross the threshold that triggers response. The silence we hear is conditional, not permanent. The paradox dissolves into waiting. From their perspective, there is no contradiction at all. They know of us, but we are not yet ready. And then, there is the most unsettling possibility of all, that the silence is deliberate suppression. If a galactic community exists, perhaps it enforces quiet as a survival strategy. Perhaps it censors signals, dismantles reckless probes, or quarantines species that broadcast too loudly. In this version, silence is not natural, but imposed. The zoo hypothesis becomes not just a metaphor, but a policy. If true, then aliens already know us, but their knowledge is matched by power, and their silence is the result of rules we do not understand. For us, each possibility carries consequences. If silence means rarity, then our responsibility is enormous. We may be one of the few voices the galaxy will ever produce. To squander that by self-destruction would be a tragedy of cosmic proportions. If silence means danger, then prudence is required. We should think carefully before transmitting powerful messages, before sending probes with unencrypted information about our biology and location. We may not know who is listening or what they intend. If silence means choice, then patience is required. Perhaps one day the watchers will reveal themselves, but until then, our task is to survive long enough to meet them. The paradox thus becomes less about them and more about us. How we interpret the silence will guide how we act. Do we treat it as a warning, urging caution in how we expand and communicate? Do we treat it as an invitation, motivating us to search harder, to send messages, to launch probes of our own? Do we treat it as a mystery, reminding us that our ignorance is vast and that humility must accompany ambition? Each path carries risks and rewards, and none can be chosen lightly. Science offers tools, but not certainties. The probabilities in the Drake equation can be updated, the search strategies refined, the telescopes improved. But even if the data grows, the paradox may remain, because it is not only a scientific puzzle but a philosophical one. It asks not only whether others exist, but what we expect of them, and what they might expect of us. It is as much about values as about numbers. The weight of silence is therefore not a void but a presence. It shapes our imagination, our politics, and our future choices. It is a riddle written in starlight, reminding us that expectation is not evidence, and that knowledge comes slowly, through patient searching and cautious reasoning. The paradox does not end with an answer, it ends with responsibility. And that responsibility leads directly to the next chapter. If aliens already know about us, and if their silence is deliberate or accidental, we must still decide how to act. What risks should we consider? What ethics should guide us? How should governments and scientists prepare for the possibility of contact, whether sudden or gradual? The Fermi paradox leaves us with silence, but silence is not the end of the story. It is the threshold to questions of policy, morality, and survival. That threshold is where we step next. If aliens already know about us, the question is not only what they might do, but how we should act in the face of possibility. The silence of the stars gives us no certainty, but it does not remove responsibility. Even without proof, our broadcasts and probes already announce our presence. We are visible, and perhaps observed. What matters is whether we are prepared to face the consequences of being known. Risk is the first reality. Contact with an extraterrestrial civilization would be the most profound moment in human history, yet it could also be the most dangerous. The range of outcomes spans the sublime and the catastrophic. A message from the stars could unite humanity in awe or fracture it in fear. A probe drifting in our skies could be a gift of knowledge or a Trojan horse. History warns us that contact between unequal cultures is rarely gentle. When advanced societies on Earth met those with less technology, the result was often collapse for the weaker side, even when conquest was not intended. Diseases spread, worldviews shattered, cultures unraveled. The gap between humans and extraterrestrials would be greater still. Their very existence could destabilize us before a word is exchanged. Protocols exist, but they are fragile. The International Academy of Astronautics and the SETI Institute have drafted guidelines for post-detection scenarios, stressing verification, transparency, and restraint. If a signal is detected, it should be confirmed by independent observatories, announced publicly, and not answered without global consultation. The principles are sound. The problem is power. These guidelines are voluntary, with no force of law. In reality, a single observatory, a nation, or even a corporation could act unilaterally, claiming the right to speak for Earth. The temptation to seize prestige or advantage would be immense, and the risk of misrepresentation equally so. Debates over deliberate messaging reveal the same tension. Some argue for active SETI, urging us to send bold, carefully crafted signals to announce ourselves to the galaxy. Others warn this is reckless, exposing us to unknown dangers. To broadcast is to shout in the dark without knowing who waits. Critics invoke the precautionary principle. When the risks are immense and the probabilities unknown, restraint is wiser than boldness. We do not yet know whether the silence is benign or threatening. To gamble recklessly with the entire planet is a decision no one has the right to make alone. And yet fear must not paralyze us. Contact may bring not only danger but opportunity. A signal could contain knowledge that reshapes science. The discovery of a probe could prove that we are not alone, ending millennia of speculation. Even the detection of distant techno-signatures, industrial pollutants in an alien atmosphere, the glow of cities on a faraway night side would transform our place in the cosmos. The risks are real, but so are the rewards. The challenge is balance, openness tempered by caution, curiosity guided by humility. Concrete scenarios reveal how unprepared we are. If a narrowband signal were detected tomorrow, confirmation would be a race against rumor, and governments would scramble to decide who speaks for Earth. If a probe were discovered in the asteroid belt or at a lunar Lagrange point, nations would compete for access, fearing danger, but coveting knowledge. Even the discovery of technosignatures on an exoplanet would ripple through culture and religion, shaking foundations without firing a shot. In each case, governance would be the true test. Who decides how humanity responds? Who controls access, interpretation, and communication? Without frameworks, chaos would fill the vacuum faster than any alien signal. The silence of the stars is not permanent. Whether tomorrow or centuries hence, the possibility of contact endures, and the consequences will not respect borders. A message, detected in one nation, belongs to all. A probe found on the moon cannot be the property of one agency. The stakes demand global cooperation, yet history suggests cooperation will be hard-won. Rivalries may deepen, secrecy may tempt, and unity may fracture. But if we cannot act as one species in the face of contact, then we may squander the chance to meet the galaxy wisely. And so the politics of contact becomes the heart of the problem. Risk and ethics demand caution, but caution without preparation is still dangerous. We must think ahead, build frameworks of governance, and acknowledge our ignorance. Aliens may already know about us, but whether we are ready to know about them is our burden to carry. The silence has given us time. What we do with that time will decide whether first contact is a triumph of wisdom or a tragedy of division. The story of aliens who may already know about us is not one of certainty, but of possibility, measured against the hard limits of physics and the frailty of evidence. We have mapped the reach of our own signals, the thin bubble of radio that extends barely a century into space, no more than 100 light-years from our Sunday. Within that bubble are thousands of stars, each with its own worlds, any one of which could host listeners, capable of detecting our noise. Beyond it, our presence fades into silence, lost in the immensity of the galaxy. For all the grandeur of our broadcasts, we remain a faint whisper against the cosmic background. That is the first truth. Only those nearby could already know, and even they would know little. What could they truly learn from our leakage? A civilization with enormous radio telescopes and patience could detect the telltale patterns of artificial transmission. They would see not a single channel but a cacophony television carriers, radar pulses, satellite chatter, all smeared and weakened by distance. With sufficient integration time, they could distinguish this noise from nature. They could infer that a technological species exists on a small blue planet orbiting a yellow star. But decoding our cultural content, our voices and music, would be far harder. Signals disperse, overlap, and fade. To reconstruct a single television broadcast across dozens of light-years would demand engineering almost beyond imagination. The likely reality is that aliens nearby might detect our presence, but not our stories. They would know we are technological, but not who we are. Our atmosphere, however, reveals far more. For billions of years, oxygen and methane have announced that Earth is alive. For the last century, industrial chemicals such as chlorofluorocarbons have added a sharper technosignature, detectable in principle by advanced spectroscopy. An alien astronomer studying our planet through a giant telescope could measure these fingerprints and conclude that Earth not only harbors life, but has entered an industrial age. In this sense, aliens do not need our broadcasts to know us. Our atmosphere is a billboard we cannot turn off. It tells the story of biology and technology, of forests and factories alike. That is the second truth. Biosignatures and technosignatures are more revealing than our radio leakage. If aliens already know of us, their knowledge is therefore partial. Nearby civilizations could have logged our noise and recognized a young technological species. More distant civilizations could have charted our biosignatures for eons, aware of life, but not of intelligence. Civilizations, thousands of light years away, see Earth not as it is, but as it was. To them, we are still in the age of Rome, or the age of the dinosaurs, depending on the distance. Knowledge travels at the speed of light, and what others know of us depends on where and when they look. That is the third truth. Their knowledge of us is always delayed, and perhaps always incomplete. Speculation fills the gaps. If watchers exist, what would they do with this knowledge? They may ignore us, regarding Earth as one more curiosity among countless worlds. They may observe us silently, out of caution or ethical principle, choosing not to interfere until we prove maturity. They may have seeded probes hidden in our system, though none has been found, or they may not exist at all, and the silence may be the sound of emptiness. Each scenario has weight, but none has proof. That is the fourth truth. Silence does not tell us which answer is correct. The verdict then must be sober. Aliens may already know we exist, but what they know is limited. At most, they could detect our biosphere, our technosignatures, and the leakage of our century of radio. They cannot know our present in real time, nor our culture in detail, unless they are close and extraordinarily capable. There is no evidence of probes, no verified signals, no confirmed artifacts. The most we can say is that it is plausible some nearby civilizations have noticed us, and that many more distant ones have long known Earth is alive. To claim more is to step beyond evidence into speculation. This sober conclusion is not defeat, but clarity. It tells us where the boundary lies between science and imagination. The science says that detection is possible, but proof is lacking. The imagination says that watchers may exist, but their motives are unknowable. Between these poles, we must live, neither dismissing the wonder nor exaggerating the certainty. Humility is our compass, and yet even this modest verdict reshapes how we see ourselves. To know that our atmosphere glows with signatures visible across light years is to recognize that we are already participants in a cosmic drama, whether we like it or not. To realize that our signals form a bubble expanding ever outward, to feel the weight of our adolescence, exposed to eyes we cannot see. To acknowledge that silence endures is to confront the paradox of possibility unmet, and to accept that our choices matter. If aliens already know, they may be waiting. If they do not, then we are the first voice in a vast silence. Either way, the responsibility is ours. We must search carefully, act cautiously, and prepare wisely. We must protect our world, nurture our species, and decide what face we will show when the galaxy finally answers, or when we learn at last that it never will. The book closes not with certainty, but with wonder and restraint. We may be known, we may be watched, but proof awaits discovery. Until then, the silence is our companion, and humility our only guide.